Tonight, we're going to measure the universe, not with imagination, not with guesses, with real numbers, real distances, real scale. And what those numbers reveal, one step at a time, starting from Earth, is something the human mind is genuinely not prepared for. Because every scale you think you've understood gets swallowed by the next one, every single time. And when we finally reach the outermost edge of everything observable, what you find there is not the end of the universe. It is the end of our ability to know it. By the end of this journey, you won't just know how massive the universe is, you'll feel the weight of everything beyond it. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. We are remarkably poor judges of size, not because we lack intelligence. Our brains are extraordinary instruments, refined over hundreds of thousands of years to navigate a very specific range of scale. We understand the height of a door, the width of a river, the distance between two towns. These are the scales that kept our ancestors alive, to hunt, to migrate, to find water, to come home before dark. But the universe does not operate at the scale of a hunting ground. The moment we step beyond what our feet can walk, what our eyes can naturally see, what our hands can touch, our intuition quietly, politely steps aside. Not because we are incapable, simply because nothing in our entire evolutionary history ever required us to understand something this large. We were never built for this, and the result is a kind of permanent, inherited illusion, a feeling that the world around us is enormous, when in fact it is something far stranger. It is the smallest possible beginning. Let us start at home, the Earth, the one object in the universe no person has ever needed an introduction to. We were born here, we live here, we feel it beneath us right now. Solid, familiar, completely real, and it genuinely is large. Earth's diameter, the distance straight through the planet from one side to the other, through the core, is approximately 12,742 kilometers, or about 7,918 miles. Sit with that number for a moment. To walk all the way around the outside of Earth following the equator without deviation, you would cover approximately 40,075 kilometers, about 24,900 miles. Walking at a steady, comfortable pace, without sleeping, without stopping for food, without pausing for a single hour, that journey would take roughly 334 days, more than 11 months, walking without pause, without rest every single day, just to circle the outside of the planet we live on. That is what large actually means, measured in human terms. Now think about how much of that 40,000 kilometer planet you have personally experienced. Most people, across an entire lifetime, move through only a few hundred kilometers in any meaningful, felt sense. The street they grew up on, the towns they have visited, the roads they have driven. Even someone who has traveled widely, someone who has crossed continents and spent years in motion, may carry a genuine lived geography of perhaps a few thousand kilometers. Picture this. If Earth were shrunk down to the size of a standard basketball, about 24 centimeters across, or roughly 9.5 inches, the territory most of us have personally walked, driven and explored across an entire human lifetime would fit within a patch smaller than the tip of a single fingernail pressed against its surface. A fingernail on a basketball, and from inside, that fingernail-sized patch of lived experience, the world feels vast. This is the first illusion, and it is a powerful one because it is not a mistake. Our brains are doing exactly what they were designed to do. They are mapping the environment that matters, the environment we actually inhabit. But the design was built for a very small canvas. We experience the world through a keyhole, and because we have never once seen the door, we assume the keyhole is the whole room. The door is much, much larger than we have imagined. Think about a journey most people would consider genuinely long, crossing from one coast of a large continent to the other, from the eastern shore of the United States to the western shore, covers roughly 4,500 kilometers, or about 2,800 miles. By car, driving 10 or 11 hours a day, it takes about 4 to 5 days of serious travel. On a commercial aircraft flying at around 900 kilometers per hour, about 560 miles per hour, that same crossing takes approximately 5 hours. 5 hours in the air, and you feel that. The seat becomes uncomfortable. You shift around. You glance at the time. The distance has weight. Now scale that up. At that same aircraft speed, 900 kilometers per hour, flying without a single stop, pointing yourself east and never turning, it would take roughly 45 hours to circle the entire planet. Just under 2 full days in continuous flight. That sounds like a significant journey. Because it is. For a human being, it represents a genuine crossing of something vast. But here is where scale starts to crack. For virtually all of human history, the moon occupied a very specific place in our imagination. It was close enough to see in extraordinary detail with the naked eye. Close enough that ancient astronomers mapped its surface from the ground. Close enough that it pulls the tides of our oceans, shifts slightly in the sky each night, and moves through a cycle reliable enough that civilizations used it as a calendar. It felt, for most of human history, like our companion. Something nearby. The nearest thing to a neighbor any person on Earth had ever had. And in a cosmic sense, that is exactly what it is. It is our nearest neighbor in space, the closest object beyond our own atmosphere. But here is where the intuition quietly fails. The average distance from Earth to the Moon is approximately 384,400 kilometers, about 238,855 miles. Let us walk through what that number actually means, not just as digits on a screen, but as a real physical distance your body could understand. Remember that aircraft, the one that could circle the entire Earth in 45 hours. If we pointed it directly at the Moon and flew in a perfectly straight line at full speed without diverting, without refueling, without stopping once, we would arrive at the Moon in approximately 17.5 days. 17.5 days to reach the closest object in space, not the Sun, not the nearest star, not the edge of our solar system, just the Moon. The object so familiar we have named its craters, so close we can see its phases change from our living rooms. 17.5 days of continuous flight, and we have not yet left the neighborhood. Here is a way to feel that distance even more precisely. Light travels at approximately 300,000 kilometers per second, roughly 186,000 miles per second. That is not just the fastest thing we have built or the fastest thing we can imagine. That is the absolute speed limit of the universe, the ceiling, the physical law written into the structure of reality itself that nothing is permitted to exceed. Think of it this way: a beam of light fired through the 12,000 kilometer diameter of the Earth would complete that journey in less than a 25th of a second. You could not blink fast enough to miss it. Light crosses our entire planet while your eyelid is still beginning to move. And yet, even at that speed, even moving as fast as anything in the known universe is physically allowed to move, light takes approximately 1.3 seconds to travel from the Moon to the surface of the Earth. 1.3 seconds? That sounds like nothing. A blink. Less than a breath. But think carefully about what it means. Every time you have stood outside and looked up at the Moon, every time in your life, you are not seeing it as it exists at that moment. You are seeing it as it was 1.3 seconds ago. The light reaching your eyes had already been traveling, crossing that gap, before you noticed it arriving. The Moon you see is not the Moon that is. It is a very recent memory. It is light that left before you looked. we are already living in the past, and we have not yet left our immediate neighborhood. That gap, 384,000 kilometers between our planet and its only natural companion, felt for nearly the entire span of human existence like an uncrossable divide, a permanent boundary, the place where the known world ended. And then, on the 20th of July, 1969, 3 human beings crossed it, with computers that had less processing power than the most basic device you likely have within arm's reach right now, with guidance systems computed largely by hand, with nothing but mathematics and extraordinary engineering and something deeply and stubbornly human. They closed that distance and left footprints on another world. We had not become large. We had simply refused to be contained by our smallness. But if the moon, visible with the naked eye, familiar enough that we have mapped its mountains from the ground, close enough that human beings have walked on its surface, is already 17.5 days away by aircraft, what does that begin to suggest about everything beyond it? Here is something worth sitting with. The distance from the Earth to the Moon is already about 30 times the full diameter of Earth itself. If you lined up 30 copies of our planet edge to edge, the last one would just about reach the Moon. 30 entire Earths, side by side. And that only gets us to our nearest companion, not the Sun, which is 400 times further away than the Moon. Not the nearest star, which lies so far beyond the Sun that the comparison barely makes sense in words. Not the edge of our solar system, which extends so far beyond the planets that even our fastest spacecraft need decades to reach it. Just the Moon. One hop, the first step. And here is the image we will carry through everything that follows, because it will mean more and more as we go. If you took our entire solar system, Earth, Moon, Sun, every planet, every asteroid, every comet, the full enormous structure of our cosmic home, and compressed all of it down to the size of a single grain of dust, the observable universe would still be the size of the entire United States. We will return to that grain of dust. By the end, it will mean something entirely different than it does right now. Right now, wherever you are, the room around you, the weight of your hands, the air you are breathing without thinking, all of it rests on a planet that is itself vanishingly small against the scale we are about to enter. Not large, not a fixed point of stability, a speck, adrift in something we are only beginning to understand. And yet, here you are, noticing. Earth is not our limit. The Moon is not our limit. We have understood this, in a comfortable and unthreatening way, for decades. We know the solar system exists beyond the Moon. We have seen photographs of Saturn's rings and Neptune's storms. We have watched spacecraft depart and never return. The knowledge sits quietly in the back of the mind, familiar, unthreatening. But knowing the solar system exists and truly feeling its scale are entirely different things. Because when we move outward from the Moon, into the deeper architecture of our own solar neighborhood, toward the Sun, toward the outer planets, toward the true outer boundary of the system that holds us, the numbers do not simply grow larger. They begin to shatter the framework entirely. We left Earth behind. We crossed the Moon. We felt the first crack in our sense of what large actually means. And now we are moving outward into our own solar system. The place we think we know. The place every schoolroom diagram has shown us, tidy and proportional, planets spaced evenly around the Sun. That diagram has been lying to us for a long time. Every one of us grew up with an image of the solar system. 8 planets, 9 if you remember a time before, arranged in neat, evenly spaced rings around a central sun. Mercury close in, Venus next, then Earth, then Mars, a comfortable gap, then the outer planets, Jupiter, Saturn with its rings, Uranus, Neptune, lined up with satisfying regularity. The image is in textbooks, on classroom walls. in every documentary we have ever seen. Familiar, logical, intuitive. And it is almost completely wrong. Not wrong about the order, not wrong about which planets exist. Wrong about the single most important thing any diagram is supposed to show: the actual distances between things, the real spacing, the true emptiness between each world. Every single diagram of the solar system you have ever seen has compressed the distances by a factor of thousands to make everything fit on a single page. If any diagram had been drawn to actual scale, with the Sun the size of a tennis ball, Mercury would be about 3 meters away, roughly 10 feet. That much feels manageable, but Neptune, the outermost major planet, would be over 215 meters from that tennis ball. That is the length of 2 full football fields. You would need a space the size of 3 city blocks just to hold the outer edge of our solar neighborhood, and the paper holding the diagram would need to be blank for almost all of that distance, because that is what the solar system actually is. Mostly nothing, vast, unimaginable silent emptiness, with tiny worlds separated by distances that break the frameworks we use to think about space. Let us start with the Sun. Step outside on a clear day and let sunlight fall on your face. That warmth, immediate, familiar, the most ordinary sensation in a human life, traveled approximately 150 million kilometers, or about 93 million miles, to reach you. Every photon of light landing on your skin right now left the surface of the Sun about 8 minutes and 20 seconds ago. Not an hour ago, not yesterday. 8 minutes. On a cosmic scale, that is close, practically next door. But here is where our intuition begins to fail us, even for something this familiar. The Sun is not the modest, moderately sized star our daily experience suggests. The Sun's diameter, across its full width, is approximately 1,392,000 kilometers, about 865,000 miles across. That number is almost impossible to hold in the mind as a real physical thing, so let us translate it into something the body can grasp. If the Sun were hollow, completely hollow, like a vast spherical shell, approximately 1,300,000 Earths could fit inside it. Not 100, not 10,000, 1,300,000 entire planets, the size of the one you are sitting on right now. And yet, as stars go, the Sun is not large, not even close to the largest. Astronomers classify it as a medium-sized, rather average star. There are stars in our galaxy so enormous that if one were placed at the center of our solar system, its surface would extend past the orbit of Jupiter. Stars so large that the Sun itself would vanish inside them, like a marble dropped into a cathedral. We will return to that. For now, let us stay in our neighborhood and understand the distance first. The distance from Earth to the Sun, 150 million kilometers, 93 million miles, has a name in astronomy. Scientists call it 1 astronomical unit, or 1 AU. Astronomical unit is simply a convenient measuring stick, the average distance from the Earth to the Sun, used as a unit to describe distances within the solar system. Instead of writing out 150 million kilometers every time, astronomers say 1 AU. At that distance, light, the fastest thing that can exist, takes 8 minutes and 20 seconds to reach us. Think carefully about what that means. Every sunrise you have ever seen, every afternoon on a beach, every time light came through a window in the morning, that light was not instantaneous. The Sun you were looking at was not the Sun as it existed at that moment. You were seeing an image of the Sun as it was 8 minutes and 20 seconds earlier. By the time any light from the Sun arrives at your eyes, 8.5 minutes of time have already passed on its surface without your knowledge. If the Sun were somehow to simply vanish, not that this will happen, simply as a thought, the Earth would continue orbiting in complete darkness for 8.5 minutes before we had any way of knowing. We do not watch the universe as it is. we watch a delayed record of what it was. Now, let us take that distance, 1 AU, and begin walking outward through the solar system. Picture this. We are going to compress the entire solar system down to the size of a small courtyard, say about 200 meters across, roughly 2 football fields laid end to end. In this compressed model, the Sun sits at one end. At this scale, the Sun is about the size of a large grapefruit, maybe 14 centimeters across, just over 5 inches. Where is Earth in this model? About 15 meters away from the Sun. Not at the far end of the courtyard, not halfway down. 15 meters. The length of a modest living room, roughly. That is our entire Earth-Sun distance compressed. And at this scale, the Earth itself, our entire world, is about the size of a sesame seed. Invisible, unless you were looking for it. A sesame seed, 15 meters from a grapefruit. Now keep walking. Mars sits about 23 meters from the Sun in this model, still in the near end of the courtyard. Jupiter, the largest planet in the solar system, large enough to fit over 1,300 Earths inside it, sits about 78 meters from the Sun. At this scale, Jupiter is about the size of a small marble. A marble 78 meters from a grapefruit. Saturn, with all its extraordinary rings, sits at about 140 meters, near the far end of our courtyard. And Neptune, the outermost major planet, the edge of what most people think of as the solar system, sits 450 meters away, more than twice the length of our entire courtyard. We have already run out of space. The model needs to be significantly larger than we imagined to hold just the 8 planets. But here is what makes this truly staggering. Neptune is not the edge of the solar system. Most people, including most scientifically literate people, assume the solar system ends somewhere around Neptune, or perhaps Pluto just beyond it. The planets run out, and so the solar system ends. This makes intuitive sense. When the major structures stop, the system stops. But the reality is very different, and not slightly different. Dramatically, shatteringly different. The true outer boundary of the solar system is a vast, spherical shell of icy bodies and frozen debris that surrounds the Sun at enormous distance. Astronomers call it the Oort cloud. The name belongs to the Dutch astronomer Jan Oort, who proposed its existence in 1950. The Oort cloud is the source of many long-period comets, the slow, spectacular visitors that occasionally fall inward toward the Sun after spending millions of years in frozen silence at the outer edge of the system. No spacecraft has ever reached the Oort cloud. No instrument has directly imaged it. Its existence is inferred from the paths of comets that arrive from its direction, but it is considered one of the most well-supported structures in solar system science, accepted by NASA, the ESA, and the broader astronomical community. Now here is where the number fractures everything. The inner edge of the Oort cloud begins at approximately 2,000 astronomical units from the Sun, 2,000 times the Earth-Sun distance. The outer edge extends to somewhere between 50,000 and 100,000 astronomical units. Let us take the middle estimate, roughly 50,000 astronomical units. Remember our courtyard model, where Neptune sat 450 meters away? In that same model, the outer edge of the Oort cloud, the true edge of our solar system, would sit approximately 750 kilometers away, about 466 miles. That is not across a courtyard. That is not across a city. That is the distance from one major city to another. London to Edinburgh, New York to Pittsburgh, all of it belonging to a single star system, our star system, and the planets, those 8 familiar worlds, would occupy only the first 450 meters of that 750-kilometer expanse. Less than 1% of the solar system's true diameter contains every planet we have ever known. We have actually tried to cross this distance. Not all of it, not even close, but we have tried. In 1977, NASA launched 2 spacecraft called Voyager 1 and Voyager 2. These remain the farthest human-made objects in existence. Voyager 1, as of current tracking, has been travelling through space for nearly 50 years. At the moment we speak, it is moving at approximately 17 kilometers per second, roughly 61,000 kilometers per hour, or about 38,000 miles per hour. A speed so extreme that it would cross the United States from coast to coast in less than 3 minutes. And at that speed, travelling continuously for half a century, Voyager 1 has covered approximately 25 billion kilometers, or about 15 billion miles. That sounds extraordinary. Because it is extraordinary for a human-built machine. 50 years of continuous travel, faster than anything we have ever launched, and Voyager 1 has not yet reached the inner edge of the Oort cloud. At current speed, it will take Voyager 1 an estimated 300 years just to reach the Oort cloud's inner boundary, and another 30,000 years to pass through and exit the other side. 30,000 years. When Voyager 1 finally clears our own solar system, human civilization as we recognize it will likely look as different from today as today looks from the Stone Age. Empires will have risen and fallen, languages will have changed beyond recognition, and a small metal spacecraft launched by 23 humans in 1977 will still be crossing the outer boundary of our local neighborhood. Now apply the reverse. We took the solar system, a structure so enormous that our fastest spacecraft cannot cross it in a human lifetime, and shrank it to a grain of dust. The single grain of dust we introduced in our last conversation. If our entire solar system, from the Sun to the outermost edge of the Oort cloud, were compressed to the size of a grain of sand, a real grain of sand, the kind you brush off your palm at a beach, then the distance to the nearest star beyond our Sun would still be only a few millimeters away. Not the nearest galaxy, not the edge of the observable universe, the nearest individual star, a few millimeters from a grain of sand. And our galaxy, the Milky Way, the home that contains our solar system along with hundreds of billions of other stars, would be the size of a large sports stadium or a few city blocks. We are not even at the beginning of the beginning. But before you allow that thought to diminish you, sit with its opposite for a moment. Within this one grain of dust, on the third sesame seed out from a grapefruit, on a world surrounded by frozen silence in every direction, something happened that has not been confirmed to have happened anywhere else in the known universe. Life, mind, the capacity to look outward and understand, the capacity to do exactly what you are doing right now. That grain of dust is not small because it is insignificant. That grain of dust is extraordinary because something inside it learned how to measure everything outside it. And yet, if our solar system, with everything it contains, occupies less than a grain of sand in the larger picture, what does that make the distance to the next star, the next sun, the nearest point of light in that black ocean beyond the Oort cloud? We have now crossed our own solar system in our minds. We have felt what those distances truly mean. We understand, in a way that no diagram on a classroom wall has ever communicated, that our solar system is not a cozy cluster of worlds. It is an ocean of void, enormous beyond anything our daily lives prepare us for, with a few small specks of rock and gas floating in its darkness. And yet, when we take that entire ocean, the Sun, all 8 planets, the asteroid belts, the Oort cloud, every comet and moonlet and frozen rock in the system, and measure it against the distance to the next star, our solar system shrinks to something that barely registers, because the distance between our solar system and Proxima Centauri, the nearest star beyond our Sun, is not twice the solar system's width, not 10 times, not 100 times. It is something so much larger than that we need an entirely new unit of measurement just to talk about it without losing our minds. And that distance, that first step outside our own system, is where the story of scale truly starts to crack open. We crossed the solar system. We felt what those distances meant in our bodies, not just our minds, We saw our entire planetary neighborhood compressed to less than a grain of sand, and now we step outside it. One step, the nearest star, the first gap between suns. What we find there does not widen the picture, it shatters the frame entirely. The nearest star to our sun is so far away that no human technology ever built, traveling at its maximum speed without pause, could reach it within a single human civilization. Not a generation, not a dynasty, not the entire recorded span of human history from the first written word to this moment. Not even close. The star we are talking about is called Proxima Centauri. It sits within the Alpha Centauri system, a cluster of 3 stars that, from Earth, appears as one of the brightest points in the southern night sky. Close enough to be seen with the naked eye, bright enough that ancient navigators used it to orient their ships. And Proxima Centauri is the nearest of the 3, the closest star to our Sun anywhere in the known universe. The distance between our Sun and Proxima Centauri is approximately 4.24 light-years. A light-year is the distance that light, travelling at 300,000 kilometers per second, the absolute speed limit of the universe, covers in a full year of continuous travel. 1 light-year equals approximately 9.5 trillion kilometers, or roughly 5.9 trillion miles, 9.5 trillion, to cross just 1 light-year, and Proxima is 4.24 of those. Now let us feel what 4.24 light-years actually means, not as a number, as a physical experience of distance, the kind your body understands. Start simply. Walking. If you could somehow walk through space, which you cannot, but follow the thought, at a comfortable human pace of about 5 kilometers per hour, roughly 3 miles per hour, the kind of pace you might use crossing a city on a quiet afternoon, the journey would take approximately 900 million years to reach Proxima Centauri. 900 million years ago, Earth had no land animals, no forests, no fish. The most complex life on the planet was multicellular organisms drifting in ancient seas. Walking at a comfortable pace without pause from that moment in deep prehistory, you would arrive at Proxima Centauri roughly now. We are not walking. Take a commercial aircraft instead. A modern passenger jet cruising at around 900 kilometers per hour, 560 miles per hour. Flying continuously, no stops, no refueling, pointed directly at Proxima Centauri. The journey would take approximately 5 million years. 5 million years ago, the first upright walking hominids were just beginning to leave footprints in the soft volcanic ash of East Africa. Our entire evolutionary lineage, every ancestor between those early bipedal creatures and the person watching this right now, would play out in the time it takes a commercial plane to reach the nearest star. Still not there. Now, Voyager 1, our fastest outbound spacecraft, launched in 1977, currently travelling at approximately 17 kilometers per second, about 61,200 kilometers per hour, or 38,000 miles per hour. A speed so extreme it would cross the continental United States in about 2.5 minutes. At that speed, the pinnacle of human propulsion across half a century of effort, the journey to Proxima Centauri would take approximately 74,000 years. 74,000 years ago, the Toba supervolcano in what is now Sumatra erupted in the largest volcanic event the Earth had experienced in 2 million years. Some researchers believe the resulting climate disruption pushed the entire human population to the edge of survival, that humanity at that moment may have been reduced to only a few thousand individuals. Every human being alive today descends from a population that may have been smaller at that point than the audience of a modest concert hall. If Voyager had been launched in that moment of near extinction, it would be arriving at Proxima Centauri approximately now. That is not a journey we can make, not with anything we have built, not in any time frame that belongs to a human civilization. And if 74,000 years is what it takes simply to reach our nearest neighbor, what does that begin to tell us about the distances between all the other stars? the hundreds of billions of them scattered across the galaxy. Picture this. We are going to build a scale model of the Sun and its nearest neighbour using objects you can hold in your hand. Take a standard basketball and place it on the ground in front of you. That basketball represents the Sun, our star, the centre of our solar system, in perfect proportion to reality. At this scale, every measurement in this model is faithful to the actual distances involved. Now, where does Proxima Centauri, the nearest star, the closest Sun, belong in this model? Not across the room, not across the building, not across the city. The second basketball, representing Proxima Centauri, would need to be placed approximately 6,900 kilometers away from the first one, about 4,300 miles. Roughly the distance between New York and Moscow. 2 basketballs, one in New York and one in Moscow, representing the 2 nearest stars to each other in our corner of the galaxy. And between them, in that 6,900 kilometer stretch of space between the 2 balls, nothing, absolutely nothing, no planets, no gas, no dust worth mentioning, just the cold, unbroken, structureless void, the most common substance in the universe, and the one that every diagram has spent decades carefully hiding from us. Right now, wherever you are sitting, whatever surrounds you, the light coming through a window or the quiet of an evening room, you are enclosed in something. Walls, air, atmosphere, a planet beneath you, a star warming you from 93 million miles away. You are never truly alone in space because you are embedded inside a solar system, inside a galaxy, inside a structure of matter and energy that holds everything together. But in the gap between our Sun and Proxima Centauri, none of that is true. In that 6,900 kilometer stretch between 2 basketballs, in the real universe, no warmth reaches from either direction in any meaningful quantity. No gravity holds you to anything. No light reaches you bright enough to read by. You float in a darkness that is not dramatic, not threatening in any cinematic way, simply indifferent. The universe, at its default, looks like that gap, not like Earth, not like a solar system. The universe, in its most typical state, is that void. Earth is the exception. Life is the anomaly. And that distance, 4.24 light-years to the nearest star, is not unusual. Across the Milky Way galaxy, the average distance between neighbouring stars runs roughly 4 to 5 light-years. Our Sun and Proxima Centauri are not an outlier pair, widely separated by some cosmic accident. They are typical. In most of our galaxy, stars are separated from their nearest neighbours by something very close to that distance. Think about what that means for the full picture. The Milky Way contains somewhere between 100 and 400 billion stars. The uncertainty in that estimate alone is staggering, and each one of those stars sits, on average, about 4 to 5 light-years from its nearest neighbour. The galaxy is not a dense crowd of suns. It is an ocean of void, with tiny islands of light scattered across it at immense intervals. If you shrank every star in the Milky Way to the size of a grain of sand and placed them proportionally, the grains would be separated, on average, by roughly 20 kilometers, about 12 miles. Billions of grains of sand, each one 20 kilometers from the next, across a disk of space so vast, it takes light 100,000 years to cross it from edge to edge. A galaxy is not a sea of light. A galaxy is almost entirely darkness, with occasional separated sparks. Here is something that quietly fractures the intuition most of us carry without realizing it. When you look at the night sky, at the scattered brightness of stars, the human eye and brain construct a sense of proximity. The stars look close. They look arranged. They seem to cluster. The Milky Way itself appears as a band of faint, continuous light, as if the stars blur together into something solid. But that appearance is an illusion created by the limits of human eyesight. Our eyes cannot resolve individual points of light separated by light years. They merge them. They create a suggestion of density where actual density does not exist. What looks like a glowing river of stars is in reality a structure so empty that if you could teleport into the middle of the galactic disk and look around, most directions would show you only darkness. Individual stars, visible but separated by distances, requiring thousands of years of travel to cross. The night sky is not what it appears to be. What appears as richness and closeness is actually an extreme sparseness, made to look like abundance by the limitations of our perception. Here is a way to feel that emptiness with a single image. The density of matter inside the Milky Way galaxy is extraordinarily low. In the regions between stars, which represent the vast majority of the galaxy's volume, space is so empty that a cubic centimeter of it contains, on average, roughly one single atom. A single hydrogen atom, floating in a cubic centimeter of space, about the size of a sugar cube. By comparison, the air you are breathing right now contains approximately tens of billions of atoms in every cubic centimeter. Your breath is unfathomably denser than the space between stars. Your body is practically a solid wall compared to the interstellar medium, the thin, scattered matter that fills the galaxy between its suns. Space is not full. Space is almost entirely nothing. And the nothing is so profound that the matter of an entire galaxy barely registers against it. This is the moment where many people feel something deflate, as if the universe has been revealed as less than they imagined. All that emptiness, all that cold void, all that wasted space between unreachable stars. But the emptiness is not a failure of the universe. The emptiness is a condition of stability. Stars are separated by light years precisely because of gravity, the same force that holds you to the Earth, that keeps the moon in its orbit, that binds our solar system together. If stars were packed densely, their gravitational interactions would be catastrophic, destabilizing orbits, flinging planets into the cold, disrupting the long, stable eons that complex chemistry and life requires to develop. The void between the stars is not waste. The void is the distance that allowed this planet to orbit quietly for 4.5 billion years, undisturbed by the gravitational pull of a passing sun. The void is what gave evolution time to work. The void is what made you possible. The emptiness of space did not diminish life. The emptiness of space created the conditions for it. We have now traveled, in our minds, from the Earth's surface to the moon, outward through the solar system to the edge of the Oort cloud, and now beyond, to the first star, the first honest step into the interstellar void. Let us compress what we have learned into a single image. Take everything we have covered, the Earth, the moon, the sun, all 8 planets, the full sweep of the solar system out to the edge of the Oort cloud, all of it compressed to a single grain of sand. We established that in our last conversation. Now place that grain of sand on a table in front of you. The nearest star, Proxima Centauri, sits a few millimeters away from that grain. But the Milky Way galaxy, which contains 400 billion of those grains spread across a disk 100,000 light-years wide, would stretch for about 30 meters in every direction around you. And the observable universe, which contains approximately 2 trillion galaxies, each containing hundreds of billions of stars, would extend in every direction to the horizon and far, far beyond it. We are at the very first step outside our grain of sand. We have not even cleared the driveway. We now understand what a gap between 2 stars looks like, not abstractly. In our bodies, through the travel times, through the basketball model, through the image of a single atom floating in a cubic centimeter of darkness, knowing that the average gap between stars is 4 to 5 light-years of cold, empty void, the next question becomes almost impossible to hold in the mind without something giving way. Because our galaxy does not contain 2 stars, or 10, or 1,000. The Milky Way contains somewhere between 100 and 400 billion individual suns, each one separated by roughly that same 4 to 5 light-year void from its nearest neighbour, and all of it, every single star, every gap, every dark expanse of interstellar space, arranged into a single coherent structure, one island of light, one galaxy. How large does something containing 400 billion stars, each separated by light-years of emptiness, actually have to be? The answer requires us to stop thinking in distances between objects and start thinking in a number so large that we need a new kind of patience just to hold it still long enough to examine it. We have crossed the solar system. We have stood at the gap between two stars and felt what 4 light-years of emptiness actually means. We have understood in our bodies that space is mostly nothing. Now we need to understand what holds all of that nothing together. The Milky Way, our galaxy, the structure that contains our sun, our solar system, every star we have ever named. We live inside it, and we have almost no idea what it looks like. Here is the strange thing about the Milky Way. We cannot photograph it. Not really. Not from the outside. Every dramatic, sweeping image you have ever seen of a spiral galaxy, the ones with glowing arms curving outward from a bright central core, those are photographs of other galaxies, distant neighbours, separate islands of stars close enough in cosmic terms to image from afar. The Milky Way, we have never seen whole. We are inside it, buried in one of its arms, roughly halfway out from the centre, like a single cell living inside an organism it cannot step outside of to observe. Everything we know about the shape of our own galaxy, every detail of its structure, its size, its spiral arms, we have assembled the way a person might assemble a portrait of their own face having never seen a mirror, through careful measurement, inference, the patient accumulation of indirect evidence gathered by astronomers across more than a century. What they assembled is remarkable, and far larger than anyone first imagined. The Milky Way is a flat, rotating disk of stars, gas, and dust, a structure astronomers call a barred spiral galaxy, meaning it has a central bar-shaped core with arms spiraling outward from each end. Think of a pinwheel, but made of hundreds of billions of suns, rotating slowly through the dark. Its diameter, the distance from one outer edge of the disk to the other, passing through the center, runs approximately 100,000 light-years. Let us sit with that number properly. 1. Light-year, as we established, is the distance light covers in a full year of continuous travel, about 9.5 trillion kilometers, or roughly 5.9 trillion miles. Multiply that by 100,000. The Milky Way is so large that a beam of light, moving at the absolute speed limit of the universe, would take 100,000 years to cross it from edge to edge. Not 100,000 years of human travel, or spacecraft travel, 100,000 years of light travel. The fastest motion physically possible in the known universe, running without pause, would need the entirety of modern human history, repeated roughly 50 times over, just to cross our galaxy once. And that is just the flat disk. The Milky Way is also surrounded by a vast, roughly spherical region called the galactic halo, a diffuse cloud of older stars, ancient star clusters, and dark matter that extends outward well beyond the disk itself, likely for another 100,000 light-years or more in every direction. Our galaxy is not a flat coin. It is more like a fried egg, with a haze surrounding it that extends far beyond the egg itself. Now consider what fills that space. The Milky Way contains somewhere between 100 and 400 billion stars. That range, 100 to 400 billion, reflects not uncertainty about the galaxy itself, but the genuine difficulty of counting objects across 100,000 light-years, while standing inside the structure you are trying to count. Imagine being asked to count all the trees in a vast forest, while standing in the middle of it, unable to see beyond the nearest few kilometers in any direction. That is the challenge astronomers face when estimating the Milky Way's stellar population. Suppose you were given the task of counting every star in the Milky Way. 1 star per second. No sleeping, no stopping, no pausing for any reason whatsoever. You count continuously from the moment you begin. How long would it take? Take 100 billion as the lower bound. To count to 100 billion, one number per second, without pausing, without sleeping, would require approximately 3,170 years. The Roman Empire rose and collapsed. Every medieval dynasty, every Renaissance, every industrial revolution, every modern century of science, all of it would unfold while you were still counting toward the lower estimate of our galaxy's stars. And that estimate of 100 billion may itself be too low. Picture this. If the entire Milky Way was shrunk down to the size of a disk 1 meter across, about the width of a large dinner table, our solar system would sit roughly 26 centimeters from the center. Not at the edge, not at the core. Almost exactly halfway out from the center, nestled in a region astronomers call the Orion Arm, one of the galaxy's minor spiral arms. And at that scale, our entire solar system, the Sun, all 8 planets, the full sweep of the Oort cloud that we spent so much time exploring, would be a speck 5 times thinner than a single human hair. It would be utterly invisible to the naked eye. That speck is our home. That 2/100ths of a millimeter on a 1 meter disk is everything our sun has ever warmed, every world our probes have ever reached, every orbit every living thing in our solar system has ever traveled. Take a breath right now. Feel the air coming in. That single breath, that quiet, automatic rhythm your body carries out 30,000 times a day without thought, happens on a world that is currently moving through the galaxy at roughly 220 kilometers per second, about 137 miles per second, fast enough to circle Earth in less than 3 minutes. And yet, you feel none of it. No wind, no pressure, no sense of motion. The scale is so vast that even that extraordinary speed registers in the body as perfect stillness. We are not standing still. We have never been standing still. We are passengers on a planet orbiting a star, that star orbiting the center of a galaxy, the whole structure turning through space at a speed that would cross a continent in seconds. And from inside that motion, everything feels like calm. Here is where the scale acquires a kind of depth that takes a moment to fully arrive. Our Sun, carrying the Earth and everything else in our solar system, takes approximately 225 million years to complete one full orbit around the center of the Milky Way. Astronomers call this a galactic year, one complete lap around the galaxy, 225 million years. Let us anchor that in something real. The last time the Earth was in exactly the position in the galaxy that it occupies right now, the late Triassic period was just beginning. The first true dinosaurs had only recently emerged. No birds existed yet, no mammals as we would recognize them. The continents looked nothing like today. The supercontinent Pangaea was only just beginning to break apart. The Atlantic Ocean had not yet formed. The landscape of Earth was so foreign that you would not recognize a single living thing on it. And in the time since that moment, across 225 million years of life, extinction, evolution, continental drift, the rise and fall of the dinosaurs, the emergence of mammals, the entire history of our species, every civilization, every century we have ever lived, the Earth has completed exactly one orbit around the center of its own galaxy. One lap. We have been here for the blink of one galactic year, and the galaxy itself has been turning for roughly 60 galactic years since it formed. Now move toward the center. For most of human history, the center of the galaxy was simply the direction in which stars became more densely packed, a bright, diffuse glow in the constellation Sagittarius, observed but not understood. Even into the 20th century, astronomers assumed the galactic center was simply a denser region of stars. Crowded, certainly. Bright, obviously, but structurally similar to the rest of the galaxy. They were wrong. Dramatically wrong. In the 1980s and 90s, teams of astronomers, including Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, began tracking individual stars near the galactic center with increasing precision. What they were looking for was the motion of those stars. What those stars were doing would tell them what held them in such tight, fast orbits, what invisible mass was pulling them inward with such force. The answer that emerged over decades of careful measurement was extraordinary. At the very center of the Milky Way sits an object called Sagittarius A star. Not a star, despite the name. A supermassive black hole, a region of space where gravity has become so intense that not even light can escape. The mass of Sagittarius A star is approximately 4 million times the mass of our Sun. 4 million solar masses, compressed into a region smaller than our solar system. Ghez and Genzel received the Nobel Prize in Physics in 2020 for this work. In 2022, the Event Horizon Telescope, a global network of radio telescopes working together as one Earth-sized instrument, captured the first direct image of Sagittarius A star's shadow. We have now seen it, not hypothesized it. Seen it. 4 million solar masses. Compressing that number into something the body can hold. If our Sun were the size of a marble, Sagittarius A star would have the mass of a mountain range, and it sits 26,000 light-years from here. That distance, the distance from our solar system to the galactic center, is itself so enormous that light traveling from Sagittarius A star takes 26,000 years to reach us. The image the Event Horizon Telescope captured in 2022 is not an image of how that region looks today. We are seeing it as it was 26,000 years ago, when modern humans were still in the Stone Age. We might reasonably wonder what proximity to something that massive means for us, whether it poses a threat. The answer is deeply reassuring. 26,000 light-years is an extraordinary buffer. At that distance, the gravitational influence of even a 4 million solar mass black hole is vastly diluted by the square of that distance. The same mathematical principle that makes a flashlight feel faint across a dark field, though it burns bright up close. Our position in the Orion Arm is remarkably stable. Quiet. Protected from the violent, dense, radiation-rich environment near the galactic core by precisely the distance that makes it feel remote and abstract. We do not orbit close to the galactic center. We orbit where conditions allow long-term stability. We orbit where a planet can persist for 4.5 billion years without being disrupted. We are not at the center. We are at the right distance from it. And yet, for all of this, the 100,000 light-years of width, the hundreds of billions of stars, the supermassive black hole at the center, the slow 225 million-year orbit, the Milky Way is just one galaxy. How many galaxies are there? If you took the entire Milky Way, 100,000 light-years of disk, 400 billion stars, the halo, the center, and compressed it to the size of a single coin, the nearest large galaxy to our own would sit just 60 centimeters away, roughly the length of a human arm. We are not alone in the dark. We are one island in an archipelago, one galaxy among many, and the number of galaxies in the observable universe is so staggering that the Milky Way, this structure we have just spent considerable time trying to comprehend, becomes at the next, scale up, essentially invisible. We have now mapped our home galaxy in our minds, its size, its stars, its position, its center, its orbit. We have held all of it at once, and we have begun to sense that the Milky Way, for all its extraordinary scale, is simply one unit in a much larger structure. But before we zoom outward into that larger structure, before we meet the galaxies beyond our own and the forces that govern them, we need to understand something deeply unsettling about what awaits us. The Milky Way and its nearest large neighbour are not drifting peacefully apart through empty space. They are moving toward each other, and they have been for a very long time. What happens when two galaxies the size of the Milky Way collide, and what that means for everything inside them, turns out to be one of the most profound examples of how scale transforms the meaning of destruction entirely. We have our galaxy now, 100,000 light-years of stars and darkness, 400 billion suns, a supermassive black hole at the centre, pulling everything slowly around it. We are inside this. This is home. But the Milky Way is not alone. And what surrounds it, what gravitationally binds us to it, is about to complicate the word home in a way no one expected. For most of the 20th century, the picture of an expanding universe gave cosmology something that felt, quietly, like reassurance. Edwin Hubble's landmark observations in the 1920s confirmed what Einstein's equations had suggested. The universe is expanding. Galaxies are moving apart from each other, carried outward on the stretching fabric of space itself. The universe, in the broadest sense, is a place of increasing separation, of growing distance, of gradual, orderly drift. Galaxies move apart. That was the picture. That was settled. And for most galaxies, it is absolutely true, except the one aimed directly at us. Andromeda, the largest galaxy in our immediate neighbourhood, a spiral galaxy broadly similar in structure to our own Milky Way, is not moving away from us. Astronomers measuring its motion with precise spectroscopy discovered something the expanding universe picture did not prepare them for. Andromeda is approaching, moving toward the Milky Way at approximately 110 kilometers per second, about 68 miles per second, closing the distance. On a confirmed collision course, the universe expands, but some things within it fall toward each other anyway. Before we arrive at that collision, we need to understand the family we belong to. The Milky Way does not sit alone in empty space. It belongs to a gravitationally bound collection of galaxies called the local group. Gravitationally bound means these galaxies are held together by their mutual gravity, not drifting apart with the expansion of the universe, but locked in a long, slow, cosmic dance, orbiting a shared centre of mass, destined to remain together across vast spans of time. The local group contains more than 50 confirmed member galaxies. Most of them are small, dwarf galaxies, irregular smears of a few 100 million stars, huddled around the two largest members like satellite towns around a city. Two galaxies dominate the group by mass and size. One is the Milky Way, the other is Andromeda. Picture this. On a clear, moonless night, far from city lights, you step outside and look toward the constellation Andromeda in the northern sky. If your eyes have fully adjusted to the darkness, fully, after at least 20 minutes away from any light source, you can see it with the naked eye, not as a point of light, the way a star appears, as a faint, diffuse smear, a tiny, almost imperceptible oval of pale light, slightly off-center from where the eye expects a star. That smear of light is an entire galaxy, 2.5 million light-years away, the most distant object visible to the unaided human eye under dark skies. 1 trillion stars, roughly 2 to 3 times the number in our own Milky Way, compressed by distance into a patch of sky smaller than the full moon. The light reaching your eye right now from that faint smear left Andromeda 2.5 million years ago, not 2,000 years ago, not 200,000, 2.5 million. When that light began its journey toward us, modern humans did not exist. Our ancestors were Homo habilis, early stone tool users, living in East Africa, the written word still 2.5 million years in the future. That light has been travelling the entire span of human prehistory, and history to arrive at your eye on this particular night, and the galaxy it came from is still on its way toward us. Right now, in this moment, Andromeda is approximately 2.5 million light-years away, and it is roughly 110 kilometers per second closer than it was 1 second ago. You cannot feel that closing. No instrument you could build would detect the change within a human lifetime. But the closing is real, and it has been real for billions of years. Let us deal with what the word collision actually means at this scale, because our intuition about it is completely wrong, and the reality is far stranger and, in a certain way, far more beautiful. In approximately 4 billion years, current models confirm that the Milky Way and Andromeda will collide. The two galaxies will interpenetrate, their stars, gas clouds, and dark matter halos passing through and around each other over the course of hundreds of millions of years, their shapes distorted by tidal forces, their structures drawn into long streams and bridges of stars, the whole violent-looking process playing out in the slowest, grandest gravitational choreography in our cosmic neighborhood. NASA's Hubble Space Telescope team published detailed simulations of this merger in 2012, and the picture they assembled is extraordinary. Here is what will likely happen. The galaxies will pass through each other. They will swing apart. Then gravity will pull them back. They will collide again and again. Over roughly 2 billion years of repeated interaction, the two spiral galaxies will gradually coalesce, blending into a single, larger, roughly elliptical galaxy. Astronomers have informally called this merged result Milkdromeda. One galaxy, born from two. That sounds catastrophic. The word collision carries with it the weight of impact, destruction, annihilation, and the visual simulations, stars flung outward in great arcs, spiral arms distorted into chaos, look violent. But here is what actually happens to the individual stars. Almost certainly, nothing. Think of two enormous swarms of fireflies drifting slowly toward each other across a vast, dark field on a summer night. Each swarm contains billions of fireflies. As the swarms close the distance and finally interpenetrate, the swarms merge. The pattern of light shifts and blurs and rearranges. The shape of each swarm dissolves into something new. But the individual fireflies, they almost never touch. The swarm looks dense from a distance, but from inside, each firefly is separated from the next by a distance that means direct collision between any two individuals is essentially impossible. Stars are the fireflies. Galaxies are the swarms. The distance between any two neighboring stars in the Milky Way runs roughly 4 to 5 light years, tens of trillions of kilometers of empty space between each sun. When Andromeda's stars pass through the Milky Way during the merger, the probability of any individual star in our galaxy making direct contact with any individual star from Andromeda is extraordinarily small. NASA's own models confirm that the vast majority of stars in both galaxies will simply be gravitationally redirected, nudged into new orbits, flung into new paths. Without ever physically colliding, the galaxies will merge, the stars almost certainly will survive, and our Sun, along with the Earth and everything in our solar system, will most likely be one of them, carried along, redirected into a new orbit around the combined galactic center, but structurally intact. 4 billion years from now, the night sky as seen from Earth, if Earth still exists, which is not guaranteed for entirely separate reasons, will show the distorted, twisted arms of two galaxies in the slow process of becoming one. Not a catastrophe, a transformation. But what force holds all of this together? The Milky Way, Andromeda, the 50-some galaxies of the local group in a single bound structure rather than letting them all drift apart with the expanding universe? The answer is gravity. Not the simple, familiar gravity that holds us to the Earth, but gravity operating at a scale so large that it competes directly with the expansion of space itself. The local group sits inside a region where the mutual gravitational attraction of all its members, every galaxy, every star, all the gas and dust, and critically, the enormous invisible mass of dark matter that surrounds and permeates the whole structure, is strong enough to overcome the expansion of the universe locally. The space between local group galaxies is not expanding significantly. Gravity wins at this scale. The threshold between bound to each other by gravity and carried apart by cosmic expansion is one of the most profound boundaries in cosmology. Objects on one side of it will eventually drift forever apart. Objects on the other side will remain together, potentially forever, merging and interacting across timescales that dwarf anything we have discussed. The local group sits entirely on the bound side of that line. We are not isolated. We are members of something. For most of astronomy's history, the local group appeared to have two clear dominant members, the Milky Way and Andromeda, with a scattering of smaller irregular companions. The third largest member, the Triangulum Galaxy, at approximately 2.73 million light-years away, was recognized as a significant spiral galaxy in its own right, containing an estimated 40 billion stars, a genuine galaxy, but far smaller than its two giant neighbors. Around the two giants, astronomers catalogued a growing collection of dwarf galaxies, small, faint, irregular structures ranging from a few million to a few 100 million stars. The large and small Magellanic Clouds, visible from the southern hemisphere as detached patches of the Milky Way, are the most familiar examples. Satellites of our galaxy, orbiting us like small moons orbiting a planet. But here is where the picture keeps expanding. With more sensitive instruments, astronomers have continued discovering new local group members, faint dwarf galaxies, invisible to earlier surveys, keep emerging from the data. The count has climbed steadily, and current estimates suggest there may be far more ultra-faint dwarf satellites still undiscovered, too dim for current instruments to detect confidently. The local group is probably larger and more complex than the catalogue currently shows. The family is likely still being assembled, even as we study it. Here is what the local group represents when you sit with it. We are not a lonely star system. We are not even a lonely galaxy. We belong to a gravitationally bound family of galaxies that has been moving together, interacting, exchanging streams of stars, pulling each other through space across billions of years. The Milky Way has already consumed several smaller dwarf galaxies in its past, absorbed them, drawn them in, incorporated their stars into its own structure. Andromeda has done the same, and in 4 billion years, those two histories will merge into a single larger one. Everything we have called home, the Earth, the solar system, the Milky Way, has always been part of something larger than itself, not isolated, not adrift, embedded in a structure of mutual gravitational connection, moving together through the universe as part of a family that has existed since the earliest epochs of cosmic time. That connection does not make us smaller. It makes us part of something ancient and coherent and continuously evolving. We have now moved from a single planet to a moon, from a moon to a solar system, from a solar system to a galaxy, from a galaxy to a family of galaxies gravitationally bound across 10 million light-years of space. And each time, the scale has grown by a factor that makes the previous scale seem vanishingly small. But the local group, 10 million light-years across, 50-plus galaxies, 2 dominant spirals on a confirmed collision course, is itself only one small piece of the next structure up, because the local group is not alone in the cosmos either. It belongs to something larger, something whose scale requires us to abandon the word galaxy as a unit of measurement entirely, and replace it with a word that contains 100,000 galaxies the way a city contains individual rooms. And at the center of that structure something pulls, something enormous, something unnamed, something whose nature remains one of the genuine open mysteries of modern astronomy. We have a galaxy, we have a family of galaxies gravitationally bound moving together through space. We thought that was the structure. We thought that was where the nesting stopped. We were still thinking too small. The local group, 50 galaxies, 10 million light-years across, is not a freestanding structure in the universe. It is a tributary, a single thread inside something so much larger that it took until 2014 for humanity to finally see it whole. Think about the surface of the Earth for a moment, not its size, but its flow. Rain falls on a mountain somewhere in the interior of a continent. It trickles into a stream. The stream feeds a river. The river joins a larger river. And all of it, every drop across thousands of kilometers of landscape, moves in the same direction toward the same destination, drawn by the same gradient. The water does not choose. Gravity chooses for it. The entire watershed is one coherent system, organized around a single basin toward which everything flows. The universe has watersheds too, not of water, of galaxies. And our galaxy, the Milky Way, along with Andromeda, along with the entire local group, sits inside one, moving, right now, at extraordinary speed, towards something at the center of that basin. Something that has been pulling on us for billions of years. Something whose precise nature, even now, remains one of the genuine open mysteries of modern astronomy. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii published a landmark paper in the journal Nature. The paper used a new technique, mapping not just the positions of galaxies, but their velocities, the precise directions in which they were moving, to trace the gravitational flow lines of the local universe, the way a hydrologist might map a watershed by following the paths of rivers. What they found was a structure no one had previously recognized as a single coherent object. They named it Laniakea. The word comes from the Hawaiian language, meaning roughly immeasurable heaven, and the name turns out to be precisely appropriate. Laniakea is a supercluster. A supercluster is a structure one level above a cluster of galaxies, a vast, loosely bound region of space containing thousands of galaxy groups and clusters, all flowing toward a common gravitational center, forming one enormous coherent unit. The Virgo supercluster, which astronomers had previously believed was our home supercluster, turned out to be just one part of Laniakea, a single lobe of something far larger. Laniakea spans approximately 520 million light-years. 520 million light-years across. We crossed the Milky Way in 100,000. We held the local group at 10 million. Laniakea is 520 million. Let us compress that to something a room can hold. If Laniakea, all 520 million light-years of it, were shrunk to the size of a single meter, 1 meter from end to end, the local group would be about 1.9 centimeters across. Roughly the width of a fingernail pressed against one end of that meter. The Milky Way itself would be about 1/5 of a millimeter, the width of a fine human hair, invisible without magnification. And within that hair width, the Earth, the Moon, the Sun, every planet, every orbit, every living thing that has ever existed in our solar system, all of it pressed into something too small to see, inside a fingernail, inside a meter that represents only our home supercluster. That sounds like reduction. But sit with the next thought before you let it diminish you. Laniakea contains approximately 100,000 galaxies, 100,000 individual islands of stars, each containing hundreds of billions of suns, all of them moving, right now, in a coordinated flow toward the structure's gravitational center. 100,000 galaxies, organized, moving together as one thing. Listen for a moment to the sounds around you right now, whatever they are. A quiet room, traffic outside, the sound of your own breathing, or a distant television, whatever surrounds you in this moment. Everything producing those sounds, everything those sounds travel through, the air, the walls, the planet beneath them, is currently moving through space at roughly 600 kilometers per second, or about 373 miles per second, in the direction of Laniakea's gravitational center. You cannot hear that motion. You cannot feel it. No instrument in your room would register it. But it is happening continuously, has been happening for billions of years, and will continue for billions more. The ground beneath you is not still. The galaxy containing it is in flow, all of it moving towards something. Picture this. Imagine you are looking down at a vast landscape, mountains, plains, valleys, from far above. Across this entire landscape, countless rivers of light are flowing, not randomly. Every stream, every current, every trickle is moving in the same general direction, following the gravitational gradient of the landscape toward a single low point, a single basin at the center. Near the basin, the flows accelerate. Far from it, they are gentle, barely perceptible. But everything, without exception, is drawn toward the same place. That is Laniakea. The rivers are galaxies. The gravitational basin at the center is the region astronomers have called the Great Attractor, and we, along with every galaxy in our cosmic neighborhood, are one of those rivers, flowing toward it right now at a speed that would cross the distance from Earth to the Moon in less than 2 seconds. The Great Attractor. The name itself carries the weight of a genuine mystery, and that weight is earned. Astronomers have known for decades that something in the direction of the Centaurus and Norma constellations is exerting an enormous gravitational pull on our region of the universe. Not the Milky Way's gravity, not Andromeda's, something far larger, something whose gravitational influence extends across hundreds of millions of light years and draws hundreds of thousands of galaxies toward it with relentless, measurable force. The problem is where it sits. The Great Attractor lies almost directly behind the plane of the Milky Way, hidden behind the densest concentration of gas, dust, and stars in our sky. Astronomers call this obscured region the zone of avoidance. The Milky Way's own disk blocks our view so completely in that direction that optical telescopes, the kind that see visible light, detect almost nothing useful from behind it. Mapping the Great Attractor required instruments that could see through the dust, radio telescopes, X-ray observatories, infrared arrays, working patiently for decades. What they found piece by piece was a massive concentration of galaxy clusters in that direction, centered on a region astronomers call the Norma cluster, located roughly 220 million light-years away. That much is established. What is not settled is whether the Norma cluster region alone accounts for the full gravitational pull we observe. Here is where the science reaches its honest limit. We do not fully know what the Great Attractor is. Some astronomers believe the Norma cluster and its surrounding galaxy concentrations account for most of the observed gravitational flow. Others argue that a much larger structure called the Shapley supercluster, sitting several hundred million light-years beyond the Great Attractor, one of the most massive concentrations of matter in the local universe, contributes significantly to the pull, and that what we call the Great Attractor may be the combined effect of multiple overlapping gravitational sources rather than one discrete object. Both sides have evidence. Neither side has definitively resolved the question. We have been tracking the motion of hundreds of thousands of galaxies toward this region of space. We have mapped the flows, we have measured the velocities, and we still cannot say with certainty what, precisely, is pulling them, and us, with such force across such distance. That is not a failure. That is the frontier. The next generation of telescopes, instruments being built or planned right now, will map the zone of avoidance with a clarity that was impossible until recently. The answer may come within decades. The question has been waiting for a century. For most of the 20th century, the Virgo supercluster, a structure about 110 million light-years across, centered on the Virgo cluster of galaxies, was considered our home supercluster. Textbooks named it, papers cited it. The Milky Way was understood as a peripheral member of the Virgo supercluster, sitting near its outer edge. That Picture was not wrong, but it was radically incomplete. The Tully team's 2014 analysis showed that the Virgo supercluster is not a freestanding structure at all. It is simply one region within the much larger Laniakea system, one branch of the watershed feeding into the same basin as dozens of other superclusters and galaxy filaments. Our home, as we understood it, turned out to be a subdivision of something 50 times larger, not slightly larger, 50 times larger. And the boundary of Laniakea, the edge where its gravitational watershed ends and another supercluster's watershed begins, is not a wall or a boundary in any physical sense. Superclusters are not isolated objects like stars or galaxies. They are regions of gravitational influence defined by the direction of flow. Cross the watershed divide, and you are in a region whose galaxies flow toward a different attractor entirely. We live on one side of a cosmic continental divide, and we did not know that divide existed until 11 years ago. Every map of Laniakea shows the same image, a luminous branching structure that looks unmistakably like a living thing, like a lung or a coral, or the branching network of blood vessels inside a leaf held up to the light. 100,000 galaxies arranged by gravity into something that looks, from far enough away, almost organic. 520 million light years, 100,000 galaxies, a gravitational basin whose full nature remains unresolved. We are inside this. We are one galaxy among 100,000 in a structure that was only named and described in the last decade of human history. Cosmology did not know Laniakea existed as a coherent structure until 2014. We have known about it for less time than a child born that year has been alive, and yet the structure itself has been here for billions of years, quietly organizing the motion of hundreds of thousands of galaxies around a gravitational center, pulling everything in our cosmic neighborhood toward the same point, indifferent to whether we noticed. But we did notice, eventually. We built instruments sensitive enough to measure the velocity of hundreds of thousands of galaxies, patient enough to map their flows across hundreds of millions of light years, and careful enough to see the pattern that had been there all along. The universe does not announce itself. We have to look for it, and every time we look carefully enough, we find that the structure is larger, more organized, and more extraordinary than the picture we had before. Laniakea is enormous, 100,000 galaxies, 520 million light years of organized gravitational structure, flowing toward a center we cannot yet fully see. But Laniakea is not the largest structure in the universe, not even close. When astronomers began mapping the distribution of galaxies, not just in our immediate neighborhood, but across hundreds of millions, and then billions of light years in every direction, what they found was a pattern that no model had anticipated and no theory had predicted. Galaxies and galaxy clusters were not distributed randomly through space, the way dust might scatter through a room. They were arranged, connected into filaments, vast, thread-like walls of matter stretching across hundreds of millions of light years. Between those filaments, voids, enormous, almost perfectly empty regions of space so large that 100 Milky Ways placed end-to-end would not cross them. The universe, at its largest observable scales, has a structure, a single, coherent, astonishing structure, and the name astronomers eventually gave it tells you everything about how it makes you feel when you see it for the first time. We have now moved through every scale of structure we know close to home: a solar system, a galaxy, a family of galaxies, a supercluster 520 million light-years across. Each step has revealed something larger than the step before it, but we have not yet seen the universe itself, the full architecture, the largest pattern that exists. What we are about to see was not predicted, and it looks like nothing anyone imagined. At large enough scales, the common assumption was always this: the universe, however enormous, would look roughly the same in every direction. Spread matter across billions of light years, and the distribution should smooth out, the way a handful of sand thrown across a floor eventually produces a roughly even layer. No large patterns, no preferred directions, just an approximately uniform scatter of galaxies distributed more or less randomly across the dark. This was not a careless assumption. General relativity supported it. The earliest cosmological models built on Einstein's equations required it. The universe at its larger scales was expected to be essentially homogeneous, meaning the same everywhere, no special structure, no grand architecture. Scientists were confident, but the reality is very different. Not slightly different, profoundly, structurally, astonishingly different. The universe at its larger scales is not a uniform scatter of galaxies. It is a web. Astronomers call it the cosmic web. The name is precise. At scales of hundreds of millions to billions of light years, the distribution of matter across the universe forms a pattern that resembles, with striking accuracy, the structure of a three-dimensional web, or, even more accurately, the structure of foam. Imagine a handful of soap foam held up to the light. Thin walls of soap film, arranged into irregular cells, each cell a bubble enclosing empty air. The walls of the foam concentrate all the material into thin sheets and filaments. The interior of each bubble contains almost nothing. The universe has this exact structure, precisely. The walls and filaments of the cosmic web are dense concentrations of galaxies, hundreds of thousands, sometimes millions of galaxies, packed into long, thread-like structures that stretch across hundreds of millions of light years. Superclusters like Laniakea sit where these filaments intersect, the way knots form where threads in a net cross. And inside the cells, inside the bubbles, almost nothing. Vast, nearly empty regions of space that astronomers call voids. Feel the surface beneath you right now, the chair, the floor, whatever supports you in this moment. Solid, certain, present. The matter in that surface, and in your body, and in this planet, and in every star, in every galaxy we have discussed, represents a tiny fraction of the universe's volume. Roughly 80% of the observable universe's total volume consists of voids, empty space. The matter we can see, measure, and stand on occupies something closer to 20% of the volume. And even within that 20%, most of it is still mostly empty space between stars and galaxies. The universe is not full of things. The universe is almost entirely void, with thin, luminous threads of structure running through it. We exist on one thread. Within those filaments, astronomers have identified individual structures of such extraordinary size that naming them required a kind of courage, because the numbers attached to them push against the limits of credibility. In 2003, a team led by J. Richard Gott at Princeton University mapped a structure they called the Sloan Great Wall, a vast filament of galaxies stretching across approximately 1.37 billion light-years. That is 1.37 billion light-years in a single connected structure. The observable universe is roughly 93 billion light-years across, so the Sloan Great Wall spans roughly 1.5% of the full observable diameter. That sounds small, but 1.5% of 93 billion light-years is 1.37 billion. The Sloan Great Wall is so large that light, travelling continuously at the universe's speed limit, would take 1.37 billion years to cross it from end to end. When that light began its journey at one end of the structure, the most complex life on Earth was single-celled organisms in ancient seas, and then the numbers grew again. Before we arrive at what may be the largest structure ever measured, we need to understand what lies between the filaments, what the voids actually are. Picture this. Imagine you are floating in space inside the Bootes void, a roughly spherical region of space approximately 330 million light-years across, discovered in 1981 when astronomer Robert Kirshner and his colleagues noticed, to their deep confusion, that an enormous region of sky contained almost no galaxies whatsoever. Inside the Botas void, you look in every direction. No stars, no galaxies, no visible light in any direction strong enough to cast even the faintest shadow. The nearest galaxy cluster lies hundreds of millions of light years away in every direction, beyond the void's walls. The darkness around you is not the darkness between stars. It is a darkness so profound, so structurally empty, that it has a different quality entirely. A silence not of absence, but of architecture. The Botas void is large enough to contain approximately 2,000 Milky Way-sized galaxies, if they were evenly distributed at typical galactic spacing. None of them are there. Hold a piece of soap foam up to a window on a bright day. The light catches the thin walls, makes them glow, while the interior of each bubble stays perfectly dark. That is what the universe looks like from outside. Glowing threads, dark interiors, everywhere and at every scale the same pattern repeating. In 2014, a team of astronomers led by Istvan Horvath published observations of what they called the Hercules Corona Borealis Great Wall, a concentration of gamma-ray bursts, the most energetic explosions in the known universe, clustered in a region of space spanning approximately 10 billion light-years. 10 billion light-years. The observable universe is 93 billion light-years across. The Hercules Corona Borealis Great Wall, if it is indeed a single coherent structure, would span roughly 1/9 of the entire observable universe. 1/9, a single object, whose width represents a meaningful fraction of everything we can see. But here is where the science becomes genuinely unresolved, and where honesty requires us to sit with uncertainty rather than rush past it. The Hercules Corona Borealis Great Wall may be the largest structure in the observable universe, or it may not exist as a single structure at all. Some astronomers accept the Horvath team's measurements as evidence of a genuine, coherent large-scale feature, an overdensity of matter extending across 10 billion light-years, challenging the cosmological principle that the universe becomes uniform at large enough scales. Others argue that the apparent clustering of gamma-ray bursts could result from statistical noise, from incomplete data, from the limits of our detection methods, and that what looks like a single structure may simply be a chance alignment in a data set that does not yet have the resolution to distinguish pattern from coincidence. Both positions are held by serious researchers. Neither has been definitively resolved. We do not know at present whether the Hercules Corona Borealis Great Wall is real. We have the data. We have two competing interpretations of it, and the instruments that might settle the question, deeper surveys, more complete gamma-ray burst catalogues, are still being built and operated. This is what the frontier of science actually looks like. Not certainty, not resolution. A genuine question, openly held, waiting for more light. Here is what makes the cosmic web even more extraordinary than its sheer size. The filaments, the walls, the voids, all of this structure, organized across billions of light years, did not come from anything large. It came from something almost infinitely small. In the earliest moments after the Big Bang, the universe was not perfectly uniform. Tiny quantum fluctuations, variations in density so minute they operated at scales smaller than an atom, created regions where matter was ever so slightly more concentrated than neighboring regions. Not by much, by a fraction of a percent. But gravity is patient. Over hundreds of millions of years, then billions of years, those tiny initial overdensities attracted more matter. Slightly denser regions pulled in surrounding material. The slightly denser became denser still. The slightly emptier became emptier still. Over time, cosmic time, billions of years of relentless gravitational accumulation, those microscopic quantum ripples in the early universe amplified into the filaments, walls and voids we observe today. Every galaxy in every filament of the cosmic web traces its origin to a quantum fluctuation so small it had no physical dimension we can meaningfully describe. The largest structures in the observable universe grew directly from the smallest possible variations in the earliest possible conditions. The universe wrote its architecture in quantum ink, and gravity spent 13 billion years completing the drawing. The filaments of the cosmic web glow faintly in maps built from galaxy surveys, millions of data points assembled into a structure that, rendered visually, looks unmistakably alive. Like mycelium beneath a forest floor, like neurons firing across a mind. The resemblance is not mystical. Gravity produces branching networks. So, does biological growth? The same mathematics underlies both. The universe did not copy life. Life grew in a universe already shaped by the same physics. The cosmic web might feel, at first, like the final argument for human insignificance. We are not just small compared to a planet or a solar system or a galaxy or a supercluster. We are a microscopic point on a single filament of a web that spans the entire observable universe, a web whose individual threads are themselves larger than anything in our previous experience of scale. But consider what it means that this web exists at all. The universe did not have to be structured. A perfectly uniform distribution of matter and energy, the thermodynamically simpler outcome, would have produced no stars, no galaxies, no planets, no chemistry, no life. The tiny quantum fluctuations that seeded the cosmic web were also, in the same act, the fluctuations that eventually produced every star that ever formed, every world that ever cooled, every ocean that ever held chemistry complex enough to think. The cosmic web is not the backdrop to our existence. The cosmic web is the direct ancestor of it. Every atom in your body traces its lineage to a star. Every star traces its origin to a galaxy. Every galaxy traces its formation to a filament of the cosmic web. And every filament of the cosmic web traces its origin to a quantum fluctuation smaller than anything the human mind can genuinely picture. The structure of the entire universe leads, by an unbroken chain of physical cause and consequence, to you. We have now mapped the full visible architecture, from a single grain of sand to the filaments that span billions of light years, from the quantum fluctuations of the early universe to the walls and voids of the cosmic web. But we have been describing only what we can see, only what light can reach us from, only the observable universe, the portion of all that exists from which light has had time across 13.8 billion years to travel to our instruments. Beyond that boundary, beyond the cosmic horizon where light from the universe's beginning has only just now finished its journey to reach us, the universe continues. How far it continues, what it contains, whether it ends or whether it extends without limit, we cannot directly observe. The observable universe itself turns out to be a remarkable thing, defined not by walls or edges, but by the speed of light and the age of time. Understanding what it actually is and what lies at its boundary requires one more piece of physics that changes everything about how we think about where we are. The universe is 13.8 billion years old, so you might expect the observable universe, the region from which light has had time to reach us, to be 13.8 billion light years in radius. It is not even close, and the reason why is one of the most quietly extraordinary things in all of physics. We have been traveling outward for some time now, from Earth to Moon, from Moon to the edge of our solar system, from there across the interstellar void, through the Milky Way, beyond to Andromeda, through the local group, through Laniakea, through the cosmic web. Each step has required a larger unit of measurement, a longer period of time to cross, a deeper surrender of intuitive scale. And somewhere in the middle of that journey, a question formed, the kind that feels simple until you try to answer it properly. How far can we actually see? The answer requires us to sit still for a moment, to stop measuring distance and start measuring something stranger, the relationship between the age of the universe, the speed of light, and the expansion of space. Because those three things interact in a way that produces a result no casual reasoning prepares you for. The universe has been expanding since the beginning, not expanding into anything, space itself stretching, carrying everything within it outward. While light has been traveling toward us from the most distant sources, the universe has been expanding around that light. The source that emitted it has moved farther away. The space the light crossed has stretched behind it. And so the region we can observe today is not simply the distance light could cross in 13.8 billion years of travel. It is larger because the space behind the light was expanding the whole time the light was in transit. The result is a sphere of observable space, approximately 46.5 billion light-years in radius, a diameter of roughly 93 billion light-years, across 93 billion light-years. The universe is 13.8 billion years old, and yet the observable sphere already spans 93 billion light-years. Before we go further, the word observable needs to be understood precisely. The observable universe is not the whole universe. It is not a wall or a boundary or an edge where space ends. The observable universe is simply the region of space from which light has had enough time, given the age and expansion history of the universe, to reach us. Beyond its edge, space continues. We simply cannot receive any signal from it. Light from those regions has not yet arrived. Some of it is traveling toward us now, but will not reach us for billions of years. Some of it, from regions so distant that space expands between us faster than light can cross it, may never reach us at all. Think of it this way. You stand in the center of a very large, dark field on a foggy night. You can see to a certain distance the limit of what your light can illuminate, the limit of what the fog allows. But the field does not end at that distance. The field continues. You simply cannot see beyond it. The observable universe is that fog. The boundary is not in the universe. The boundary is in physics. In December of 1995, the Hubble Space Telescope did something that had never been done and was, by many accounts, controversial before it was attempted. Astronomer Robert Williams, then director of the Space Telescope Science Institute, decided to point Hubble at a region of sky that contained, as far as anyone could tell, essentially nothing. A small patch near the Big Dipper, chosen partly because it was relatively empty of nearby stars that might obstruct the view. Many astronomers thought the observation was a waste of precious telescope time. Point Hubble at empty space, and you would photograph emptiness. Williams proceeded anyway. For 10 consecutive days, 100 hours of total exposure time, Hubble stared at a patch of sky approximately 1/30th the diameter of the full moon, a patch so small that if you held a grain of sand at arm's length against the night sky, it would cover this entire region. When the data came back, it showed approximately 3,000 objects in that single patch. Not stars, galaxies. Each one a separate island of hundreds of billions of stars, at distances ranging from hundreds of millions to more than 10 billion light-years away. A grain of sand held at arm's length, 3,000 galaxies behind it. Williams and the team published the image in 1996. It became, and remains, one of the most consequential photographs in the history of science. Subsequent deep field observations, the Hubble Ultra Deep Field, the Hubble Extreme Deep Field, and observations by the James Webb Space Telescope, have confirmed and extended the picture. Every patch of sky, no matter how apparently empty, contains galaxies, extending to the edge of the observable universe. Think about your eyes right now, the physical sensation of seeing whatever is in front of you. The light entering them at this moment left its sources fractions of a second ago. The lamp across the room, the screen you are watching, even sunlight reflected off a wall originated 8 minutes ago at the sun. Your eyes, right now, are instruments for receiving ancient light. Every photon that enters them carries information about when and where it left its source. The Hubble Space Telescope is the same instrument, scaled to the universe. Every image it captures is a record of light that left its source millions or billions of years in the past. A photograph not of how things are, but of how things were at the moment the light began its journey. The deeper Hubble looked, the further back in time it saw. The most distant galaxies in the deep field images are seen as they were when the universe was only a few 100 million years old, young, hot, irregular, nothing like the ordered spiral structures we know nearby. We are not just looking across space, we are looking across time. The Hubble Deep Field images, combined with systematic galaxy surveys across the full sky, allowed astronomers to construct an estimate of the total number of galaxies within the observable universe. In 2016, a team led by Christopher Consolis at the University of Nottingham published a revised figure in the Astrophysical Journal. Their analysis, using the deepest available data and correcting for the many faint and small galaxies too dim for current instruments to detect directly, arrived at an estimate of approximately 2 trillion galaxies within the observable universe. 2 trillion, 2 million individual island universes, each containing hundreds of billions of stars. Let us walk through what that number means in human time. Suppose you were given the task of simply naming each galaxy, one per second, without stopping, without sleep, every second of every day. How long would it take to get through all 2 trillion? 2 trillion seconds. Divide by 60, roughly 33 billion minutes. Divide by 60 again, roughly 555 million hours. Divide by 24, about 23 million days. Divide by 365, approximately 63,000 years. 63,000 years of continuous counting, one galaxy per second, to simply name every galaxy currently estimated within the observable universe alone. When you began that count, the last ice age was ending. Agriculture did not yet exist. Writing would not be invented for another 58,000 years. You would finish counting sometime around now, having started before any civilization, any city, any written word in human history. And that count covers only what we can observe. The light reaching us from the most distant galaxies in the deep field images left its source when the universe was less than 1 billion years old. That light has been travelling for over 13 billion years. It crossed the entire span of Earth's existence twice over, before arriving at a mirror in low Earth orbit and forming an image smaller than a thumbnail. Here is something that quietly reverses the intuition built over the whole of our journey. We might expect, reasonably logically, that as time passes and the universe ages, the observable universe grows. More time means light from more distant regions has had time to reach us. The horizon expands. We see more. And in one sense, that is true. In the very short term of a human lifetime, the observable radius does technically grow slightly. But here is where it gets strange. Dark energy, the mysterious force causing the expansion of the universe to accelerate, is pushing distant galaxies away from us at increasing speed. In the very far future, the most distant galaxies we can currently observe will be receding from us so fast that new light from them can no longer reach us. Their light, trying to cross an expanding gulf, will never arrive. They will cross what physicists call the cosmic event horizon, the boundary beyond which nothing can ever reach us, and disappear from our observable universe forever. Astronomers like Abraham Loeb at Harvard have calculated the timeline. In roughly 2 trillion years, virtually every galaxy currently visible outside our local group will have receded beyond the cosmic horizon. The night sky of that future era will show only the merged remnant of the Milky Way and Andromeda, Milkdromeda, and a handful of gravitationally bound neighbours. The cosmic web, Laniakea, the 2 trillion galaxies, the filaments spanning billions of light years. All of it will be invisible, not because it ceased to exist, but because dark energy carried it beyond the reach of any possible observation. We are living in an extraordinarily privileged moment in cosmic time. Any civilization that arises more than 1 trillion years from now, if any arise at all, will have no access to evidence that other galaxies exist. They will have no way to measure the expansion of the universe because there will be nothing left to measure the expansion against. They will have no cosmic web to map, no Hubble deep field of distant light to examine, no redshift of distant galaxies to observe. The entire cosmological picture that we have assembled, the picture that tells us about the Big Bang, the expansion of space, the large-scale structure of the universe, will be permanently inaccessible to them. We built that picture now, in this specific window of cosmic time, when the evidence is still present, still reachable, still arriving at our instruments. The understanding you are gaining right now, in this moment, represents knowledge that will eventually become structurally unavailable to any future intelligence. Not lost because we failed to preserve it, lost because the universe physically removed the evidence. We see it because we are here now. And beyond the observable horizon, beyond the 46.5 billion light-year radius we can access, we do not know what exists. We do not know how large the total universe is. We do not know whether it is finite or infinite. We do not know whether the structures visible in our observable sphere, the filaments, the voids, the cosmic web, continue beyond the horizon in the same pattern, or transform into something entirely different, or repeat in some vast cycle we cannot detect. Some cosmological models suggest the universe is at least 10 times larger than the observable sphere. Others suggest it may be infinite. The data required to distinguish between these possibilities is, by definition, beyond what any instrument can collect. This is not a gap that better technology will close. The horizon is a fundamental limit, built into the physics of light, space, and expansion. No telescope we could build, no matter how large or sensitive, can receive information from beyond the distance at which the recession of space exceeds the speed of light. We are not simply waiting for the next breakthrough. We are at the hard edge of what observation in principle can ever reach. What lies beyond it is real. We simply cannot know what it is. There is a version of this moment that feels like confinement. We are trapped inside a sphere we cannot see beyond, surrounded by a darkness that physics has permanently closed off from our instruments. But consider what we did with the sphere we have, starting from a planet no larger than a sesame seed, in a model of our solar system, a species that existed for only a fraction of cosmic time, built instruments sensitive enough to photograph 3,000 galaxies behind a grain of sand. We measured the age of the universe. We mapped 2 trillion galaxies. We traced the cosmic web across billions of light years. We determined the precise radius of the observable universe and understood why it is larger than the age of the universe would naively suggest. We did not escape the horizon. We understood everything inside it. The boundary does not diminish what lies within it. 2 trillion galaxies, 200 billion stars each, in a sphere 93 billion light-years across, all of it assembled from quantum fluctuations smaller than an atom, and a single species on a single grain of dust managed to see it, map it, and comprehend it. The limit of observation is real. The scope of what we observed within that limit is extraordinary. We have now reached the observable boundary, the edge of what light can tell us. 2 trillion galaxies, 93 billion light-years, the full architecture of the cosmic web, all of it mapped within the sphere we can reach. And here is where the picture should be complete. Here is where we should be able to say, we know what the universe is made of. We have counted the matter. We have measured the structure, but here is the problem. When astronomers actually calculated how much matter, real, normal, atom-based matter, exists inside the observable universe, the total came to something deeply unsettling. All the galaxies, all the stars, all the gas, all the planets, every atom of everything we have ever detected or mapped or measured, everything visible, everything that emits or reflects light in any wavelength, represents approximately 5% of the total energy content of the observable universe. 5%. The other 95% is something we cannot see, cannot touch, cannot detect directly with any instrument currently built. Two entirely different kinds of something. One that shapes the structure of every galaxy we have ever mapped. One that is accelerating the expansion of the entire universe. Both completely invisible, both completely unidentified. We map the 5%. We have almost no idea what the other 95 is. Everything we have discussed so far, every galaxy, every filament, every supercluster, every grain of dust in our grain of dust solar system, belongs to the same category of thing: normal matter, atoms, stuff you can, in principle, touch. And that entire category, everything we have mapped, everything we have named, everything visible at any wavelength to any instrument ever built, represents approximately 5% of what the universe actually contains. 95% of the universe is made of things we cannot see, cannot touch, and have never directly detected. Not 95% of the distant, unreachable universe. 95% of the universe right here. The space around you, the space inside the Milky Way, the space between galaxies, all of it almost entirely composed of something that passes through every instrument we have ever built without leaving a single measurable trace. Let us state the composition plainly, because the numbers deserve to land without decoration. Of the total energy content of the observable universe, approximately 5% consists of normal matter. Atoms, molecules, protons, neutrons, everything that makes up stars, planets, gas clouds, human beings, and every other material thing ever observed or detected. 5%. Approximately 27% consists of dark matter. Dark matter is a name for something whose gravitational effects are clearly, repeatedly, and unmistakably measured, but whose physical nature remains entirely unknown. No particle detector has ever caught one. No telescope has ever imaged it. It does not emit light, reflect light, or interact with light in any detectable way. We know it exists because of what it does to the things we can see. The remaining 68% consists of dark energy. Dark energy is a name for the force or property of space itself that is causing the expansion of the universe to accelerate, growing stronger, pushing galaxies apart faster and faster with every passing billion years. Its nature is even more uncertain than dark matter's. 5% visible, 27% invisible matter, 68% invisible energy. The observable universe we have been navigating, the 2 trillion galaxies, the cosmic web, the filaments spanning billions of light years, all of it is the 5%. The first serious scientific encounter with dark matter came not from a deep field telescope or a particle detector, but from a velocity measurement. In 1933, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a massive collection of galaxies roughly 320 million light-years away. Zwicky measured the velocities at which individual galaxies within the cluster were moving. He expected those velocities to correspond to the visible mass of the cluster, the combined gravity of all the stars and gas he could see. The math was straightforward, but the galaxies were moving far too fast. Not slightly fast, dramatically fast. The visible mass of the cluster was nowhere near sufficient to gravitationally hold galaxies moving at those speeds together. By Zwicky's calculation, the cluster should have long since flown apart. And yet it was intact, organized, coherent. Something invisible, some additional mass providing additional gravitational binding, had to be there. Zwicky called it Dunkel Materie, dark matter. For decades, the scientific community did not fully accept it. One observation, one astronomer, one cluster. Perhaps an error in the measurements, perhaps a flaw in the reasoning. And then, In the 1970s, Vera Rubin changed everything. Rubin, working at the Carnegie Institution of Washington, spent years carefully measuring the rotation speeds of stars at different distances from the centers of galaxies. The prediction from Newtonian gravity, the same gravity that governs planetary orbits in our solar system, was clear. Stars far from the galactic center, where most of the visible mass concentrates, should orbit more slowly than stars near the center. The same way the outer planets of our solar system orbit the Sun more slowly than the inner ones. That is not what Rubin found. Across galaxy after galaxy, the rotation curves were flat. Stars in the outer regions of galaxies were orbiting at roughly the same speed as stars near the center, sometimes even faster than expected. The velocity did not drop off with distance at all. The only explanation consistent with the data was that galaxies were embedded in vast, roughly spherical halos of invisible mass, extending far beyond the visible disk of stars and gas, contributing enormous additional gravity that kept the outer stars moving at the speeds they did. The visible galaxy was not the whole galaxy. The visible galaxy was, in a sense, only the bright core of something much larger and entirely invisible. Picture this. You are hovering in space, looking at a spiral galaxy from above, the luminous disk of stars and gas, the bright core, the spiral arms sweeping outward. That visible structure spans perhaps 100,000 light-years across. Now expand your view. Extend your perception outward. 200,000 light-years from the center. 300,000. 500,000. 1,000,000 light-years. In all that vast surrounding space, no stars, no visible gas, no light of any kind. And yet, permeating every cubic meter of that invisible expanse, something exerts gravitational force, something with mass, something present, real, and physically effective, shaping the galaxy you can see, holding its outer stars in their orbits, determining the large-scale structure of everything around it. That surrounding envelope, that dark, enormous, gravitationally active halo, is likely far larger than the visible galaxy it surrounds. And every galaxy in the observable universe sits inside one. A galaxy, from the outside, looks like a luminous disk, a flat, glowing structure with a bright core and sweeping arms. But the real object, including its dark matter halo, would be more like a glowing spark inside a vast, invisible cloud. The spark is what we see. The cloud is what holds the universe together. For decades after Hubble's discovery of universal expansion, the working assumption in cosmology was reasonable and well supported. The universe is expanding. The expansion began at the Big Bang, carrying matter outward in every direction. Gravity, the mutual attraction of all that matter, must be slowing that expansion down. The expansion is decelerating. The only question was whether gravity would eventually halt it entirely, causing the universe to collapse back on itself, or whether the expansion would slow but continue forever. Both possibilities were studied seriously. Cosmologists developed precise predictions for how the deceleration should look in. The data, observing the most distant supernovae, stellar explosions whose brightness could be used as a cosmic yardstick, would measure that deceleration precisely. The answer seemed close. In 1998, two independent teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees at Harvard, published results from their supernova surveys simultaneously. They were wrong. Not about the expansion, about the direction. The distant supernovae were fainter than the models predicted. Not brighter, fainter. That meant they were farther away than expected. The universe was not decelerating under the pull of gravity. The expansion of the universe was accelerating. Something was pushing space apart faster and faster, growing stronger over time, working directly against gravity across the largest scales. Neither team had anticipated it. No model had predicted it. The entire theoretical framework for the fate of The universe had to be rebuilt from the ground up in a single year. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for this discovery. The force driving the acceleration was named dark energy, and its nature remains the largest single unsolved problem in physics today. Dark energy does not behave like a force in any familiar sense. It does not push objects the way wind pushes a sail, does not radiate the way heat radiates from a fire. It appears to be a property of space itself, something that emerges from the vacuum, from emptiness, growing in effect as space expands, as if the universe's own growth feeds the force accelerating that growth. The question of what dark matter actually is, what particle or class of particles produces its gravitational effects, remains genuinely open, with real disagreement between serious researchers. One major family of candidates involves particles beyond the standard model of particle physics, specifically a class called WIMPs, or weakly interacting massive particles, which would have mass and respond to gravity, but interact only extremely weakly with normal matter. Decades of increasingly sensitive detectors have searched for WIMPs without confirmation. They have not been ruled out, but they have not been found. Another family of candidates involves axions, a different hypothetical particle, lighter than WIMPs, proposed originally for an unrelated problem in particle physics, but later identified as a potential dark matter candidate. Multiple axion searches are underway globally. A separate school of thought called Modified Newtonian Dynamics, or MOND, proposes that dark matter does not exist as a substance at all, that instead the laws of gravity themselves behave differently at very low accelerations, and that this modification explains rotation curves without invoking invisible mass. MOND explains galaxy rotation curves well. It struggles to explain the large-scale structure of the cosmic web and certain gravitational lensing observations, where dark matter models perform better. Neither framework explains everything, neither has been eliminated. The debate is genuine, ongoing, and unresolved. We are made of the 5%. Every atom in your body, every star you have ever looked at, every instrument ever built to study the universe, all of it, the entire domain of normal matter, exists as a thin, luminous skin on a universe whose dominant constituents remain unidentified. This could feel like humiliation. The universe barely notices what we are made of. But consider what that 5% managed to do. From that thin, luminous skin, matter organized itself into galaxies, stars, chemistry, biology, and eventually a form of life complex enough to measure the 95% it cannot directly touch. We cannot see dark matter, but we map the shape of its halos from the motion of stars. We cannot detect dark energy, but we measured its existence from the faintness of supernovae billions of light years away. We did not need to be made of the whole universe to understand the whole universe. The 5% looked outward, built instruments, gathered patience, and deduced the shape of what it could not see. That, in its own way, is more extraordinary than the 95%. 5% visible, 27% invisible matter, 68% invisible energy, a universe whose dominant components have no confirmed explanation in physics. And still, we have been describing only the observable universe, the sphere of 93 billion light-years from which light has had time to reach us. Beyond that horizon, the universe continues. How far it continues, what structures it contains, whether the numbers and the physics we have measured here apply everywhere within it, we cannot know from observation alone. But physics does not stop at the horizon. Cosmological models reach beyond it. And what some of those models suggest about the universe beyond what we can see is either the most audacious idea in the history of science, or a measure of how far our imagination has been willing to follow the mathematics into the dark. We have reached the edge of what observation can tell us. 93 billion light-years of observable universe, 2 trillion galaxies, a cosmos 95% invisible, expanding at accelerating speed, its largest structures still debated, its fundamental composition still unresolved. And now the question changes entirely. Not what can we see, but what might exist beyond what we can ever see. This is where physics ends, and where mathematics, carefully wielded, takes one more careful step into the dark. There is a particular kind of limit that is different from all others. Some limits are practical. We cannot walk to the moon, but the moon exists. Someone has been there. The distance is measurable. Some limits are technological. We cannot image a planet orbiting a star 10,000 light-years away with current instruments. But better instruments might close that gap. These are limits of reach, not of principle. The horizon of the observable universe is a different kind of limit entirely. Beyond approximately 46.5 billion light-years from where we sit, the recession of space has carried regions so far that no signal from them, no light, no gravity wave, no information of any kind, can ever reach us. Not yet, not eventually, not with any instrument, not ever. The universe beyond our horizon is not hidden behind fog that better tools might penetrate. The information is not travelling slowly, it is simply not travelling toward us at all. Space between us and those regions expands faster than light can cross it. The separation grows permanently. Whatever exists out there, we cannot, in principle, ever observe it. And yet, physics does not stop at the horizon. The same equations that describe everything we have measured, everything we have mapped, everything we have traced from quantum fluctuations to cosmic web, those same equations continue outward, beyond the boundary, into the unobservable. And what they suggest, under certain conditions, is extraordinary. Before we follow the mathematics beyond the horizon, we need one piece of confirmed physics. The geometry of space, whether the universe curves back on itself like the surface of a sphere, or curves away like a saddle or lies perfectly flat, can be measured from the light of the cosmic microwave background. The cosmic microwave background is the faint afterglow of the Big Bang, ancient light, released about 380,000 years after the universe's beginning, still travelling through space today and detectable as a faint, uniform warmth in every direction. Mapped precisely by ESA's Planck satellite, it encodes information about the geometry of the universe in the slight variations of its temperature across the sky. The Planck data, published in 2018, indicates that the universe is geometrically flat to a precision of roughly 0.4%. Flat, meaning parallel lines extended indefinitely, remain parallel. Space does not curve back on itself like the surface of a sphere. The implication of a flat geometry, taken at face value, is straightforward and remarkable. If the universe is geometrically flat, and if it is not bounded by some edge or wall, if the spatial flatness extends without limit, then the universe is likely infinite, not merely very large. Infinite, not infinite in the way a number grows large. Infinite in the sense that space genuinely continues in every direction, without end. No wall, no edge, no final galaxy, just more, forever. An infinite universe, filled with matter distributed by the same physical laws that govern our observable sphere, produces a consequence that most people encounter only once and then carry quietly for the rest of their lives. In an infinite universe, with a finite number of possible arrangements of matter within any given volume, because quantum mechanics places real limits on how many distinct configurations can exist within a finite region of space, statistical repetition becomes mathematically inevitable. Let us approach this carefully, because it deserves precision. Your observable universe, everything within the 46.5 billion light-year sphere we have explored, contains a finite number of atoms in a finite number of possible arrangements. That number is almost incomprehensibly large. But in an infinite universe, any finite number occurs infinitely many times. separated by distances that dwarf everything we have discussed. The cosmologist and physicist Max Tegmark at MIT has published estimates of the approximate distance to the nearest region of space that should, statistically, contain an arrangement of matter identical to the one in our observable universe, including an identical Earth, an identical solar system, an identical you, reading or watching this same content. The distance is approximately 10 to the power of 10 to the power of 118 meters. That number has no human comparison that does it justice. It is so large that writing it out in full would require more digits than there are atoms in the observable universe. The distance is, for all practical purposes, unreachable and unimaginable. But in a genuinely infinite universe, Tegmark's argument holds that distance exists. That region, and infinitely many others like it, would be out there, unreachable, unobservable, but real if the universe is truly infinite and the physics is what we believe it to be. This is not confirmed. The universe's infinite extent cannot be directly verified, but it is the logical consequence of our best supported geometric measurement applied consistently. Picture this. In the first fraction of the first second after the Big Bang, a time span so brief it makes a nanosecond look geological, the universe underwent a period of extraordinary expansion called cosmic inflation. Inflation means not simply that the universe was expanding, but that it was expanding at a rate that doubled the size of space itself in intervals almost too small to name, again and again, in rapid succession. You cannot feel this from inside it, because there is no inside in the ordinary sense yet. Space itself is the thing that is growing, but imagine every distance in the universe simultaneously stretching, not matter moving through space, space itself inflating, carrying everything within it outward, smoothing out any irregularities, flattening the geometry, creating the vast, even, geometrically flat arena that we now measure 13.8 billion years later. Inflation lasted for an extraordinarily short time, likely ending within the first tiny fractions of the first second of the universe's existence. But in that time, regions of space that were once in contact, close enough for light to cross between them, were pushed so far apart that they can no longer communicate. They became causally separate, independent, each containing its own observable horizon. Our observable universe is one of those regions. The inflation ended here, but in some theoretical models, it may never end everywhere. In 1981, physicist Alan Guth at MIT proposed the theory of cosmic inflation to solve several otherwise puzzling features of the universe. Why it is so flat, why it looks so uniform in every direction, why certain structures are absent that earlier models predicted should exist. Inflation solved all of these problems remarkably well. The evidence for an inflationary episode in the early universe is considered strong by most cosmologists, though the precise mechanism remains an area of active research. But in the 1980s, the Russian physicist Andrei Linder developed an extension of inflation called eternal inflation. Eternal inflation, the idea that quantum fluctuations in the inflating field can cause inflation to end in some regions while continuing in others, indefinitely, leads to a picture in which new regions of space constantly bud off from the inflating background, each becoming a separate universe with its own properties, its own physical constants, potentially its own laws of physics. If eternal inflation is correct, our observable universe, the entire 93 billion light-year sphere we have explored, is one bubble in an endless foam of bubbles, each a separate universe, each cut off from all others by the relentlessly inflating space between them. Unreachable, unobservable, but, in this framework, real. This is the inflationary multiverse, and separately, arising from an entirely different branch of physics, quantum mechanics offers its own version. The boundary between our observable universe and whatever lies beyond it has no physical marker, no wall, no color change, no temperature gradient, no edge you could approach and touch. Space there is identical to space here, and yet, across that boundary, information from the other side has never reached us, and never will. In 1957, a Princeton graduate student named Hugh Everett III proposed a radical interpretation of quantum mechanics that most physicists at the time quietly set aside, and that has steadily gained serious consideration in the decades since. Quantum mechanics describes the behavior of particles at the smallest scales, and its predictions are the most precisely confirmed in the history of science. But it contains a puzzle. When a quantum system, an electron, a photon, any quantum object, is in a superposition of states, meaning it exists in multiple possible conditions simultaneously, observation causes that superposition to resolve into a single outcome. An electron that was simultaneously spinning up and spinning down resolves to one or the other when measured. Everett's proposal was that the superposition never actually collapses. Instead, the universe branches. Each possible outcome occurs in a separate branch of reality that becomes inaccessible to the others. Every quantum event, every measurement, every interaction at the quantum level generates branching, an incalculable number of branches, an incalculable number of parallel realities continuously diverging. If Everett's interpretation is correct, the number of parallel universes generated by quantum branching is not just large, it is generated continuously at every moment, everywhere, by every quantum interaction in every particle, everywhere in the universe. The majority of physicists accept the predictions of quantum mechanics completely. The interpretation, whether those branches are real, remains genuinely contested. Some physicists find the many worlds interpretation the most mathematically natural reading of the equations. Others argue it introduces unverifiable complexity without explanatory gain. The debate is real, unresolved, and conducted at the highest levels of theoretical physics. Notice your heartbeat right now, that quiet, reliable percussion somewhere behind your sternum. Each beat is a moment. Each moment contains quantum events occurring in the atoms of your body. In the many worlds interpretation, each of those events branches the universe. In the inflation picture, your entire history unfolds inside one bubble among an infinite sea of bubbles. Both frameworks are theoretical. Both follow from the same physics that produced everything else described in this script. Here is where we must be careful and honest. The inflationary multiverse, the quantum many-worlds interpretation, the Tegmark infinite universe. These are all frameworks built from real, well-tested physics, extended by legitimate mathematics into domains that observation cannot reach. They are not speculation in the loose sense. They are the careful, rigorous consequences of taking our best supported theories seriously in their full mathematical form. But they share one property that places them in a category apart from everything else discussed in this script. They are not testable, not with any instrument currently conceived, not perhaps with any instrument that could ever be built. The defining characteristic of a scientific theory, what distinguishes it from philosophy, from mythology, from beautiful speculation, is the ability to make predictions that observation can confirm or refute. The multiverse, in its various forms, makes predictions about regions of reality that no observation can reach by definition. Some physicists argue that this places it outside the domain of science. Others argue that mathematical consistency and explanatory power are sufficient to grant it scientific standing, even without direct verification. This debate about what science is permitted to claim, about the limits of the scientific method itself, is ongoing. It involves serious, distinguished thinkers on both sides. Neither position has prevailed. We do not know whether the universe is infinite. We do not know whether other universes exist. We do not know whether the branching reality of quantum mechanics is literal or interpretive. We do not know whether eternal inflation is the correct framework for what happened in the first moments of cosmic time. What we know is that our best physics, applied at its limits, produces these possibilities, that the evidence we have gathered, the flatness of geometry, the quantum behavior of matter, the dynamics of inflation, is consistent with frameworks far larger and stranger than the observable universe we have mapped. The universe may be far greater than anything we can see, not slightly greater, incomparably, perhaps infinitely greater, and we have no tool that can reach it. That is not a failure. That is the shape of knowledge at its frontier. Every age of science has had a boundary beyond which it could not see, and every generation that pushed that boundary found something extraordinary waiting just past it. The next boundary may never yield, or it may yield in ways no one currently living can predict. The existence of a limit to what we can know is not the same as a limit to what matters. We exist inside the observable universe. Everything we love, everyone we have ever known, every experience the human species has ever recorded, all of it lives within the 46.5 billion light years we can reach. Every discovery that has ever changed a human life, every work of art, every scientific breakthrough, every moment of genuine understanding, it all happened here in the 5% of the observable universe that consists of normal matter on a planet that would be invisible from the nearest galaxy. Whether the universe beyond our horizon is infinite, or whether other universes exist, does not diminish what happened inside ours. The meaning of a human life is not measured in light years. The significance of understanding, of genuinely grasping where we are, what we are part of, how extraordinary the conditions of our existence are, does not depend on the universe being finite. We exist at the edge of what can be known. That edge is not a wall, it is a window, and through it we have seen more than anyone in the history of this planet was ever able to see before. We have now travelled as far as any mind can travel, from Earth to the Moon, to the edge of the solar system, to the nearest star, across the Milky Way, through the local group, through Laniakea, through the cosmic web to the observable horizon, through the invisible universe, and now to the boundary of what observation itself can ever reach. And through all of it, through every scale, every distance, every staggering expansion of frame, one thing has remained unchanged, the place where all of this is being understood. A planet, one planet, a single unremarkable world orbiting an ordinary star in the outer spiral arm of one galaxy among 2 trillion. A world so small that in every compression model we have built, it disappears long before the model gets large enough to show anything interesting. And on that world, something happened that has not been confirmed to have happened anywhere else in the universe we have mapped. Something became aware of the rest of it. We need to sit with that for a moment, not rush past it, not use it as a transition to the next scale. Just sit with it, because it may be the most important fact in this entire journey. We have travelled a very long way together, from the ground beneath your feet to the moon, from the moon to the edge of our solar system, from there across the abyss between stars, through the Milky Way, beyond it to Andromeda, through the local group, through Laniakea, through the cosmic web, to the edge of the observable universe, and then as far as mathematics can reach beyond it. And now we come back, all the way back to here. The reasonable conclusion from everything we have covered is this: we are nothing, a species that has existed for an eye blink of cosmic time on a planet invisible at galactic scale, in a solar system that vanishes inside a grain of dust when the observable universe is the size of the entire United States. A species made of the 5%, living on the 5%, knowing almost nothing about the 95% that surrounds it on every side. The reasonable conclusion is smallness, insignificance, irrelevance. That conclusion is wrong. Not wrong because we are physically large. We are not. Not wrong because we are cosmically central. We are not that either. Wrong because it confuses scale with meaning. Wrong because it assumes that rarity and smallness point in the same direction. They do not. Let us begin with a single number, stated plainly, and then felt properly. The universe is approximately 13.8 billion years old. Modern humans, Homo sapiens, our species, not our evolutionary ancestors, but us, have existed for approximately 300,000 years. 300,000 years out of 13.8 billion. Let us walk through what that fraction means. 13.8 billion divided by 300,000 gives us roughly 46,000. Our entire species' existence, from the first Homo sapiens in Africa to every civilization that has ever risen, every language ever spoken, every child ever born, represents approximately 1/46,000th of cosmic time. 1/46,000th. If the entire age of the universe were compressed into a single calendar year, 1 year, January through December, modern humans would appear at roughly 11:52 p.m. on December 31st, with about 8 minutes remaining in the year. That is how recently we arrived, and within those 8 final minutes, written language, the first clay tablets of Sumer, the very beginning of recorded human history, appears in the last 12 seconds of the year. Every city, every empire, every book, every scientific discovery, every mapped galaxy, everything described in this entire journey from Earth to the edge of the observable universe. All of it accomplished in the last 12 seconds of a 13.8 billion year story. You are made of stardust, not as a metaphor, as a literal physical fact. Every atom in your body heavier than hydrogen, the carbon in your cells, the oxygen you are breathing, the iron in your blood, the calcium in your bones, was forged inside the nuclear furnaces of stars that lived and died before our sun was born. Those stars ran out of fuel. They collapsed. They exploded. They scattered their interiors across the galaxy. That scattered material eventually gathered, under gravity, into the cloud that formed our sun, our planets, and eventually the molecules that assembled into you. You are the universe, locally organized. You are the material of dead stars, aware of dead stars. Here is what makes this more than a poetic observation. Across the entire observable universe, 2 trillion galaxies, each containing hundreds of billions of stars, across 93 billion light-years of space, in 13.8 billion years of time, the only location where we have confirmed the existence of life is this one. One planet. This planet. We have searched, not casually, seriously, systematically, with every instrument available. Radio surveys spanning decades, Mars probes, and rovers. The analysis of exoplanet atmospheres with increasingly sensitive spectroscopy. The James Webb Space Telescope examining the atmospheres of distant worlds for chemical signatures that life produces. Nothing confirmed, not a microbe, not a signal, not a trace of biological chemistry on any other world in the observable universe. This could change. Many scientists consider it likely that life exists elsewhere. The universe is vast, the conditions for chemistry are widespread, and we have barely begun to search. The silence so far may reflect the scale of the search problem more than the actual frequency of life. That debate is genuine and unresolved, but the confirmed fact, stated plainly, remains. The only place in the observable universe where we know for certain that matter became aware, became capable of thought, of curiosity, of building instruments to look back at the stars it came from, is here, on a planet that would be invisible from the nearest galaxy, on a world smaller than a sesame seed in the model where our solar system is a grain of sand. Picture this. You are sitting somewhere right now, a room, a chair, a particular position of your body in a particular place on Earth. Around you, walls or sky, a familiar space. Beneath you, a planet 12,742 kilometers, roughly 7,900 miles, across. That planet orbits a star 150 million kilometers, or 93 million miles, from its surface. That star sits 26,000 light-years from the center of a galaxy 100,000 light-years wide. That galaxy belongs to a family of 50-some galaxies, gravitationally bound, moving together toward a common center. That family sits within a supercluster 520 million light-years across, flowing toward an attractor whose full nature we do not yet know. That supercluster is one knot in a cosmic web of filaments and voids extending across billions of light-years. All of that sits within an observable universe 93 billion light-years across, containing 2 trillion galaxies, 95% of whose total content remains unidentified. And the awareness that just followed that entire chain, from a chair in a room to the edge of what can ever be known, lives inside the chair, inside you, wherever you are right now, whatever light surrounds you, whatever temperature the air carries, whatever sounds reach you in this moment. You are in the most complex arrangement of matter known to exist anywhere in the universe we have mapped. Not the largest, not the most energetic, not the most ancient, the most complex. A human brain contains approximately 86 billion neurons, roughly 86 billion, though estimates range, each connected to thousands of others, forming a network of roughly 100 trillion connections, a structure so densely organized that some physicists have noted it approaches and may exceed the complexity of any known astronomical object of comparable size. The most intricate thing we have found in the universe is not a black hole, not a supercluster, not the cosmic web. The most intricate thing we have found is inside the skull of a species that arrived in the last 8 minutes of cosmic time. Take a moment here, not to learn anything new, not to receive another scale comparison, just to be here. We have traveled from the ground beneath your feet to the limits of what any mind can reach, and you followed the whole way. That journey took patience and a willingness to let the familiar grow strange, and then to let the strange become something that makes the familiar feel different. You did that. Sit with the fact that you just understood, in one unbroken thread, the structure of the universe from a grain of sand to the boundary of the observable cosmos. That understanding exists nowhere else in the known universe except in the minds of those who have sought it, including yours, right now. That is not a small thing. That is a rare thing. Early in this journey, we built a model. We took our entire solar system, the Sun, all 8 planets, the full sweep of the Oort cloud stretching into the dark, and compressed it to the size of a single grain of dust. And in that model, the observable universe was the size of the entire United States. We used that image as the beginning of a scale lesson, a way to feel how small our solar system is against the full extent of what exists. But here, at the end, that grain of dust means something entirely different than it did at the beginning. That grain of dust is where something happened that has no confirmed counterpart anywhere else across that massive continent, in that entire 93 billion light-year expanse, with its 2 trillion galaxies, its filaments and voids, its dark matter halos and superclusters, and invisible accelerating expansion. In all of that, one grain of dust produced something that learned to look up and understand the world around it. Not most of it, not the 95%, not even yet the full 5%, but enough of it to know that it was small, to know what small means, to know the distance to the nearest star, and the age of the oldest light, and the shape of the structures that gravity built across billions of years. The grain of dust is not small because it is insignificant. The grain of dust is extraordinary because something inside it became curious. The existence of awareness in this particular grain of dust is fragile, remarkably fragile. Earth sits in what astronomers call the habitable zone, the narrow range of distances from a star where liquid water can exist on a surface. Too close, and oceans boil. Too far, and they freeze. The zone exists, but it is not wide. Earth also sits far enough from the galactic center to avoid the intense radiation and gravitational disruptions of that crowded region, but close enough to contain the heavier elements that chemistry and biology require. The timing of our sun's formation, the particular mix of elements available in the early solar system, the presence of a large moon that stabilizes Earth's axial tilt, the list of conditions that contributed to this outcome is long. Whether those conditions are common or rare elsewhere in the universe, whether awareness is a common outcome of sufficiently complex chemistry or an extraordinarily improbable accident, we genuinely do not know. The question remains open. What we know is that here, on this particular grain of dust, the conditions aligned. The chemistry worked, time was granted, and out of 4.5 billion years of geological and biological process, matter organized itself into something capable of this conversation. That could be ordinary, it could be nearly unique. We do not know which, but it happened, and the fact that it happened at all, regardless of how common or rare it proves to be, is the most remarkable thing we have encountered anywhere in this entire journey. The physicist Carl Sagan wrote that we are a way for the cosmos to know itself. That observation, made decades ago, has not become less true with time. If anything, the deeper we map the universe, the more precisely it describes what has happened here. The atoms now organized into your body were forged in stellar interiors, in nuclear reactions at the hearts of stars that burned for millions or billions of years before our sun was born. Those atoms scattered across space in stellar winds and supernova explosions. They drifted through the interstellar medium. Gravity gathered them into a new generation of stars and planets. On one of those planets, they assembled into chemistry, then into biology, then into cells, then into nervous systems, then into a brain capable of tracing the history of those atoms back to the stars that made them. The universe spent 13.8 billion years building the conditions for that knowledge, and then, in the last 8 minutes of its history so far, it produced something that used those conditions to understand what had been built. We are not observers of the universe from outside it. We are the universe, examining itself from within. The curiosity you brought to this journey is not separate from the thing being studied. The awareness following this sentence is made of the same matter, governed by the same physics, continuous with the same story that began 13.8 billion years ago in conditions of extraordinary heat and density. That is not metaphor. That is physics. You are a local continuation of the universe's history, a region where matter became briefly, improbably, remarkably aware of its own existence. The next time you stand under a clear, dark sky and look up, really look, past the familiar patterns and into the depth, you are not separate from what you are seeing. The light arriving at your eyes came from objects that share your history. The atoms that built those stars also built you. You are looking at family. The universe is vast, incomprehensibly vast, and we have spent this entire journey confirming exactly how much that word understates the case. The universe is mostly empty, not the dramatic emptiness of a dark room, but the structural, architectural emptiness of space between stars, between galaxies, between filaments, the emptiness that makes up roughly 80% of the observable universe's volume. The universe is mostly invisible. 95% of its total content moves through the cosmos, without producing a single photon that any instrument we have ever built has caught. Dark matter shapes every galaxy we have ever photographed. Dark energy accelerates the expansion of everything we can see. Both remain, at their core, unidentified. The universe is still unfolding, still expanding, still producing stars in some regions, still assembling structure in others, still evolving toward an ending that lies so far in the future that any comparison to human timescales becomes meaningless. And through all of that, the vastness, the emptiness, the invisibility, the ongoing becoming, something in the 5% on one grain of dust, in the last 8 minutes of 13.8 billion years, looked outward and began to understand, not completely, not permanently, not without error or revision or the humility to say repeatedly that we do not know, but genuinely, honestly, with instruments built from curiosity and mathematics and the accumulated patience of generations of human inquiry. We do not fully see the universe. We never will. Its horizon is permanent. Its 95% may never yield to direct observation. Its full extent, finite or infinite, alone or multiplied, may lie forever beyond confirmation. And yet, here you are, aware of it, having travelled the full length of what can be, known, in a mind built from the same material as everything we travelled through. In a cosmos of darkness and distance, awareness is rare, perhaps rarer than we imagine, perhaps not, but rare enough that its presence in this particular grain of dust, in this particular fraction of cosmic time, deserves more than to be dismissed as insignificance. The universe is not asking us to be large. The universe is not asking us to last forever. The universe simply produced in us something that noticed it, and that, across all the distances and all the darkness and all the extraordinary emptiness of space, is enough to be something. We began with a grain of dust. Our entire solar system, the sun, every planet, everything we have ever touched or launched or named, compressed to a single grain of dust, and the observable universe around it, the size of the entire United States. That grain of dust is where you live, and somehow, from inside that grain, you just cross the whole country. Not with a spacecraft, not with a telescope, with something the universe spent 13.8 billion years building quietly without announcement, a mind, a curious, persistent, deeply human mind that refused to accept the horizon as a final answer. But right now, in this specific, irreplaceable moment, you exist, you understand. You looked at the scale of everything and did not look away. That is not what nothing does. The universe made you from its oldest material, placed you at the edge of its own comprehension, and waited to see if you would look up. You did. And now the journey is over. You are going to go to sleep tonight, and tomorrow you will wake up and the ordinary world will be waiting. The same responsibilities, the same coffee, the same ceiling above the same room. Everything will look exactly as it did before, but something will be different. Because now you know what that ceiling is. Above it, the moon. Beyond that, the sun. Beyond that, 400 billion stars turning slowly in the dark. Beyond that, 2 trillion galaxies, each one ancient, each one vast, each one indifferent to whether anyone ever noticed it. And yet, here you are, having noticed. The universe did not need you to understand it, but you did anyway. And somewhere in that, in the simple, stubborn, deeply human act of wanting to know, something remarkable happened tonight. The universe understood itself through you. Thank you for traveling this far with us.